The universe is not just vast, it's deeply weird. For every familiar planet or glowing star, there are objects so strange, they feel like they've stepped out of a movie. Imagine a world where it rains shards of glass sideways at thousands of kilometers per hour, or a galaxy held together almost entirely by invisible matter. These aren't thought experiments or wild theories. They're real discoveries, found out there in the night sky. Each time astronomers build a new telescope or send a probe into space, the universe reveals something unexpected. Let's journey through a range of some of the strangest cosmic objects ever found, from tiny frozen relics near Earth to the largest structures in existence. Oumuamua, the interstellar visitor that shouldn't exist. In the autumn of 2017, astronomers noticed a faint dot among the stars, one of the countless objects drifting across the night. But as researchers tracked it more closely, they realized it was moving too fast, far faster than anything that could have formed within our own solar system. This discovery marked the first time humanity had ever confirmed the passage of an interstellar object, a true visitor from beyond our cosmic neighborhood. It was given a name from Hawaiian, Oumuamua, which means a messenger from afar arriving first. The name itself carried a sense of mystery and importance, as though it was not just another rock in space, but a messenger with secrets yet to be understood. From the very beginning, Oumuamua refused to fit into the categories astronomers usually rely on. Objects in our solar system, like asteroids or comets, tend to follow certain rules. They have familiar shapes, clear paths, and predictable behaviors when they approach the sun. But this visitor broke the rules. Its speed alone showed it was not bound to the sun's gravity. It came rushing into the solar system, swung around our star, and then began heading back into the depths of space, never to return. This made it different from anything astronomers had ever tracked before. The more scientists observed, the stranger it became. Unlike the round or irregular shapes of most known asteroids, Oumuamua appeared long and narrow, almost like a cigar or perhaps a flat pancake, depending on how it was viewed. Its brightness fluctuated as it spun, suggesting it was tumbling end over end. That spin was itself unusual, not smooth like most rotating objects, but uneven, as if it were rolling chaotically. This alone was enough to make it stand out, but what truly caught attention was the way it moved through space. Normally, when comets pass close to the sun, the heat causes ice within them to vaporize, creating a tail of gas and dust that pushes them slightly off course. This small boost, known as outgassing, can explain why comets sometimes accelerate unexpectedly. But Oumuamua did not show the kind of visible tail that comets produce. There was no cloud of dust, no glowing stream trailing behind it. Yet, strangely, its path showed that it was indeed being nudged by something, accelerating in a way that could not be explained by gravity alone. Some researchers suggested that perhaps it was covered in a thin layer of unusual ice that released gas without leaving a visible trace. Others argued that its surface could be made of materials we had never seen before, capable of responding to sunlight in ways unlike typical comets or asteroids. The puzzle was made even harder by the fact that Oumuamua was already on its way out of the solar system when it was discovered. Astronomers only had a short window of time, just a few weeks, to gather data before it became too faint to study. In that limited time, they could not get detailed images, only faint readings of light and motion. As often happens when the unknown enters science, the gap between evidence and certainty was filled with bold ideas. One of the most talked about suggestions came from the possibility that Oumuamua might not be natural at all. Could it have been a probe, a spacecraft sent intentionally or unintentionally from another civilization? This idea was put forward in part because the way it accelerated reminded some scientists of how a solar sail, a thin sheet pushed by the pressure of starlight, might behave. If Oumuamua were such a structure, it could explain the odd movement without requiring jets of gas or dust. This possibility ignited a debate that spread well beyond the scientific community. For many, The idea of an alien probe passing silently through our solar system was both thrilling and unsettling. If it were artificial, what would that mean about life in the universe? Had another civilization sent it long ago across unimaginable distances, only for us to catch the faintest glimpse before it disappeared again? Or was this simply a case of unusual natural behavior that we had not yet learned to explain? Most astronomers leaned toward natural explanations, though none could fully solve the puzzle. Some argued that Oumuamua might be a fragment of a larger body torn apart long ago and sent drifting between the stars. Others proposed that it could be made of solid hydrogen ice, a rare material that could evaporate without leaving visible traces, giving it the odd push observed. Still, every theory came with its own challenges, and none fit perfectly. As the debates continued, the object itself slipped further away, leaving behind only questions. By early 2018, it was too faint for even the most powerful telescopes to see. It had entered our lives suddenly, stirred up confusion and wonder, and then left just as quickly, vanishing into the blackness between the stars. In its wake, it left a lasting impression. The discovery showed us that interstellar objects are real and that our solar system is not isolated but part of a larger cosmic flow. Oumuamua's brief visit also reshaped the way astronomers prepare for the future. The possibility of other interstellar visitors became an active area of study, and new observatories are being designed to scan the skies with greater sensitivity, hoping to catch the next one earlier, with more time to study. Already, another interstellar object, Comet Borisov, was discovered in 2019, though it behaved more like the comets we know. Even so, Borisov and Oumuamua together have shown that the universe is more dynamic and connected than once believed. In the end, Oumuamua may never reveal its full story. Without direct observation or a spacecraft to chase it, the mystery remains open. Its shape, its spin, and its acceleration all point to something unusual, perhaps something unique. Whether it was a fragment of alien geology or a creation of alien engineering may remain forever out of reach. It came uninvited, a silent messenger from another star system, traveling for millions of years before brushing past our sun. For a moment, humanity turned its gaze toward it, trying to make sense of the message it carried. And then it was gone, leaving behind not answers, but a deepened sense of wonder about what else might be out there, waiting to pass through our skies. Triton, Neptune's captured backward-orbiting moon. Triton, Neptune's largest moon, doesn't quite belong where it is. Most large moons in the solar system formed alongside their planets, settling into orbits that move in the same direction as their host's rotation. Triton does the opposite. It circles Neptune backward against the planet's spin. This unusual orbit is the first clue that Triton is not a native moon of Neptune, but a captured object, pulled in long ago from a wandering path through space. The capture of Triton was likely a dramatic event. To be pulled into orbit, Triton would have had to lose a great deal of energy. Scientists think this may have happened through a collision or interaction with another large object. Some believe that Triton was once part of a binary system, two large bodies orbiting one another that strayed too close to Neptune. In such a case, Neptune's gravity could have torn the pair apart, flinging one partner away while trapping Triton. This would explain why Triton ended up with such an unusual orbit, but capture is never a gentle process. The event would have thrown Neptune's early moons into chaos, likely destroying many of them. What we see today is the aftermath of that upheaval, a system reshaped by one moon's arrival. Triton is a giant compared to Neptune's other moons, measuring about 2,700 kilometers across, nearly as large as our own moon. Its size makes it one of the largest captured objects in the solar system. Many scientists think Triton originated in the Kuiper Belt, a distant region beyond Neptune filled with icy worlds and dwarf planets. Its composition and surface features fit this idea well. In fact, Triton bears a strong resemblance to Pluto, which likely comes from the same region. If true, this means Neptune's largest moon is essentially a captured dwarf planet, held prisoner by gravity since ancient times. The backward orbit is not the only thing that makes Triton stand out. It is also one of the few moons in the solar system that is still geologically active. When Voyager 2 flew past Neptune in 1989, it captured breathtaking images of Triton's surface. Instead of being heavily cratered and ancient, like many other moons, Triton showed smooth plains, ridges, and signs of resurfacing. Most surprising of all were dark geysers erupting from its icy crust. These plumes shot nitrogen gas and dark particles high into the thin atmosphere, creating streaks that stretched across the surface. This discovery was astonishing. Before Voyager, scientists expected moons that far from the Sun to be frozen and dead. But Triton proved otherwise. Even in the cold outer reaches, a moon could be alive with activity. The geysers are thought to be powered by sunlight, weak though it is at Neptune's distance. A thin layer of frozen nitrogen covers parts of Triton's surface. When sunlight penetrates this ice, it warms the ground underneath, causing nitrogen gas to build up. Eventually, the pressure becomes too much and the gas bursts out through cracks, carrying dust and ice with it. These eruptions can reach kilometers into the sky, leaving behind dark fans on the surface. It is a delicate but powerful system, showing how even a small amount of energy can drive striking activity in the outer solar system. Triton's surface itself is a patchwork of strange landscapes. There are smooth plains that appear to have been resurfaced by icy flows, ridges that stretch for hundreds of kilometers, and areas that look like a frozen version of volcanic terrain. These cryovolcanoes may have erupted liquid water, ammonia, or other substances in the past, reshaping the moon's face. Some regions appear almost like a cantaloupe rind, with deep pits and valleys giving the surface a textured look. This variety of landscapes tells us that Triton has a complex interior, one that still holds enough heat to drive geological processes. Beneath its icy shell, there may even be an ocean of liquid water, kept from freezing solid by the pull of Neptune's gravity. Because it orbits Neptune in the opposite direction of the planet's spin, Triton's orbit is slowly decaying. With each pass, gravitational interactions drain its energy, pulling it closer to Neptune. Over millions of years, this slow inward spiral will bring it to a point where it can no longer stay intact. When that time comes, Neptune's gravity will rip Triton apart, scattering its remains into space. Those fragments may form a dazzling system of rings around Neptune, possibly larger and brighter than Saturn's. In this sense, Triton is a moon with a doomed future, destined to be destroyed by the very planet that captured it. If Triton is torn apart, it will become part of Neptune's beauty rather than its companion. For now, it remains intact, but its fate reminds us that even seemingly eternal cosmic systems are temporary. What we see today is only a chapter in a much longer story of creation and destruction. The thin atmosphere of Triton, composed mostly of nitrogen with traces of methane, is tenuous compared to Earth's, but still enough to influence the surface. The atmosphere is constantly replenished by the geysers, which pump gas into the sky. Because it is so thin, it cannot hold much heat, and temperatures on Triton drop to some of the coldest measured anywhere in the solar system, around -235 degrees Celsius. Despite this, the atmosphere is active, with winds that can carry particles from the geysers and shape patterns on the ground. This makes Triton one of the few moons with both an atmosphere and active weather, even if on a small scale. Voyager 2 remains the only spacecraft to have visited Triton up close, leaving much about it a mystery. Since 1989, no mission has returned to study it in detail, though many scientists hope that one day a probe will. Triton's backward orbit, active geology and possible ocean make it one of the most fascinating worlds for exploration. A future mission could reveal whether it has conditions that might support life, even if only microbial, beneath its icy crust. If an ocean exists, it would be one of several hidden seas scattered through the outer solar system, joining the likes of Europa and Enceladus as candidates in the search for life. The idea that Neptune's largest moon was once a free-floating dwarf planet also expands our sense of the solar system's past. If Triton was captured, then other large bodies may have been pulled into or expelled from planetary systems as well. The outer solar system may have once been a chaotic arena, with worlds passing close to one another, trading places or being cast away. Triton's existence is a reminder that orbits are not always permanent, and that even large worlds can be moved by gravity's endless push and pull. Kepler 78b, a planet that orbits in just 8.5 hours. When astronomers first spotted Kepler 78b, it seemed almost too extreme to be real. A planet so close to its star that it completes a full orbit in just 8.5 hours stretches the limits of what we thought was possible for a stable world. From Earth's perspective, we're used to thinking of Mercury as the innermost planet, baking in the sun's heat, while taking 88 days to circle once around. Kepler 78b races through that journey more than 200 times faster, practically skimming the surface of its star. It is the ultimate example of a lava world, a place where the idea of solid land might not even apply, and oceans would be made of molten rock instead of water. The discovery came through the Kepler Space Telescope, which watched thousands of stars for tiny dips in brightness. These dips happened when planets crossed in front of their stars, blocking a fraction of the light. For Kepler 78b, those dips came with a rapid regularity that stunned researchers. It wasn't just fast, it was unbelievably close. The planet orbits at a distance of only about 1.7 million kilometers from its star. By comparison, Earth is about 150 million kilometers away from the Sun. Even Mercury sits at 58 million kilometers. That means Kepler 78b is nearly hugging the surface of its star. At such a distance, the temperature on the planet's surface is believed to soar above 2,000 degrees Celsius, hot enough to vaporize many metals. Any atmosphere the planet once had would have been stripped away long ago, blasted into space by radiation and stellar winds. What's left is thought to be a bare, rocky body, glowing with heat and covered in flowing lava. Astronomers call it a superheated Earth, though that description feels almost misleading. It is not Earth-like in any sense of being habitable. Instead, it offers a picture of what happens when nature pushes planetary conditions to their breaking point. The strangest part is how it got there in the first place. Planets are not supposed to form this close to their stars. In the early days of a solar system, the heat and radiation near a star are too intense for solid material to clump together. Rocky planets are expected to form farther out, where things are cooler, and then possibly migrate inward over time. How did Kepler 78b end up practically inside its star's atmosphere? One possibility is that it formed farther out and was gradually pulled in by gravitational interactions, either with other planets or with the star's disk of gas in its youth. Another possibility is that it's the surviving core of a larger planet that lost its outer layers after being dragged too close. Either way, it challenges simple models of planetary formation. Measurements suggest that it is strikingly similar to Earth in terms of mass and composition. It seems to be made of rock and iron, not light gases like Jupiter or Neptune. Yet its orbit makes it a doomed world. The immense pull of its star is slowly dragging it even closer. Over time, astronomers estimate within a few billion years, Kepler 78b may be swallowed completely. If so, it will meet its end by plunging into the very star it orbits, erased without a trace. By studying it, scientists can better understand how close-in planets evolve, how long they last, and what becomes of them. The Kepler mission has revealed that Kepler 78b isn't alone. Many other systems also contain ultra-short period planets, worlds that orbit their stars in less than a day. These systems are far more common than we once thought, which suggests that nature finds many ways to build planets in places that seem impossible. The conditions on Kepler 78b also let researchers test theories about how planets survive in such extremes. For example, the intense heat likely causes constant evaporation of material from the surface. Some astronomers have speculated that planets like this could create tails of gas and dust, similar to comets, as they lose mass. The interaction between the planet and its star might also create magnetic storms or unusual patterns in the star's light. These details are hard to detect, but future telescopes may be able to see them more clearly. For all its alien qualities, Kepler 78b also draws attention because it shares something familiar. Its size and density are so close to Earth's that it feels like a distorted twin. It shows that Earth-like planets do not always mean Earth-like conditions. A rocky world might be a paradise in one system and a furnace of destruction in another. This duality is part of what makes the search for exoplanets so exciting. Every new discovery widens the catalogue of what a planet can be. Before the 1990s, astronomers had no confirmed evidence of planets outside our solar system. Now, thousands are known and many are nothing like the worlds we grew up studying. Kepler 78b is one of the clearest signs that our picture of what planets should look like was far too narrow. The universe is not limited to copies of Earth, Jupiter, or Mars. It builds worlds that defy logic, that rewrite rules, and that keep forcing us to expand our definitions. Even though the planet itself is far too hot for life, the lessons it teaches might bring us closer to understanding habitable worlds elsewhere. It shows that planetary systems are dynamic, unpredictable, and often violent. The survival of a planet depends not just on where it forms, but on how it dances with its neighbors and its star. Psyche, the metal world that could be a planet core. Far out in the main asteroid belt between Mars and Jupiter, there is an object unlike almost anything else we know. It is called Psyche, named after the Greek goddess of the soul, and it is not a typical asteroid. While most asteroids are made of rock or ice, Psyche is composed largely of metal, iron, nickel, and other heavy elements that shine faintly in the sunlight. This makes it unique, because in many ways it looks less like a leftover rock from the solar system's formation and more like the heart of a world that never fully came to be. Astronomers believe Psyche might be the exposed core of an ancient planet. Billions of years ago, when the solar system was young, countless planetesimals, small developing worlds, were colliding, merging, and breaking apart. Some grew into the planets we see today, while others were destroyed in violent crashes. Psyche may be one of those lost bodies. At some point, it might have been a much larger world with a rocky mantle and a thin crust, but a massive collision could have stripped away those outer layers, leaving behind the metal interior. What remains now is a naked planetary core, orbiting the Sun in silent isolation. On Earth, the core lies thousands of kilometers below the surface, hidden from direct observation by layers of rock and mantle. We can only study it indirectly through seismic waves and magnetic fields. But Psyche gives us a chance to look at such a core directly. If it truly is what scientists suspect, then it could hold the answers to questions about how planets form, how their interiors evolve, and why some worlds grow to be habitable, while others remain barren. Psyche is massive compared to most asteroids. It measures about 220 kilometers across, roughly the size of the state of Massachusetts. Its surface appears to be a mixture of metal and silicate rock, with shiny regions that reflect more light than expected. Radar studies have revealed its density is lower than pure iron, meaning it may not be solid metal, but rather a porous mixture of metals and rock. Still, its composition makes it unique in the asteroid belt, a place dominated by rocky fragments and icy bodies. The idea of standing on Psyche is hard to imagine. Unlike rocky asteroids covered in dust and boulders, its landscape might be made of gleaming metal cliffs and jagged slopes, stretching across a world that has no atmosphere, no wind, and no water. Some parts of its surface may contain shiny metal plains, while others could be covered in darker rocky patches. Scientists have even speculated about what impact craters might look like on a metallic world. Instead of shattering like rock, metal might bend or deform, leaving strange shapes unseen on other planetary surfaces. This unusual nature has made Psyche the target of one of NASA's most ambitious asteroid missions. The Psyche spacecraft, launched in October 2023, is currently on its journey to reach the asteroid in the late 2020s. Its mission is to orbit and study Psyche up close, using a suite of instruments to map its surface, measure its gravity, and analyze its composition. For the first time in history, we will be able to directly explore what could be the interior of a planet-like body. One of the mission's main goals is to understand whether Psyche really is the core of a failed planet. If it is, then it represents a piece of the solar system's earliest history, frozen in time for billions of years. It would show us what the insides of rocky planets look like, offering a rare chance to test theories about planetary differentiation. The process by which heavier materials sink inward to form a core, while lighter materials float to the surface to create a crust. On Earth, this process gave rise to the iron-rich center that powers our magnetic field, a shield vital for protecting life. Psyche may show us what that process looks like in its rawest form. Another question is whether Psyche might contain evidence of unusual materials. Some researchers think the asteroid's surface could hold large amounts of valuable metals, including iron, nickel, and even platinum or gold. While this has sparked headlines about its potential trillions of dollars worth of resources, the mission is not about mining, it is about knowledge. Still, the fact that Psyche may contain so much concentrated metal raises fascinating questions about how common or rare such bodies might be, and what role they play in the story of planetary formation. The spacecraft heading towards Psyche carries a number of instruments designed to unravel its mysteries. A magnetometer will search for any remnant magnetic field, which would suggest Psyche once had a molten, active core like Earth's. Gamma-ray and neutron spectrometers will study the surface chemistry, telling us exactly what elements are present. Cameras will map the terrain in detail, revealing craters, ridges, and strange features we can only guess at today. Together, these tools will allow scientists to build a complete picture of this unusual metal world. If it were purely a core, we might expect it to be solid and extremely dense. But its measured density suggests it may be a mixture of metals and rock, or even metal with significant empty space, almost like a sponge. One theory is that it is not a pure planetary core, but a kind of hybrid body, partly melted and reformed in the chaos of the early solar system. Another idea is that it was shattered and reassembled multiple times, creating a patchwork structure unlike any other world. If it is a core, why is it exposed? If it is a mixture, what process created it? If it was shattered, how did it hold together over billions of years? By visiting it directly, we may begin to answer these questions, but we may also find answers that challenge what we thought we knew about how planets form and evolve. Psyche is a reminder of how much of the solar system remains unexplored. We often imagine that the main discoveries lie far away, around distant stars, or in the outer reaches of the cosmos. But Psyche shows that even within the familiar bounds of the asteroid belt, there are worlds that defy expectation, worlds that hold secrets about the very beginnings of planets themselves. For scientists, it is a rare chance to study a place that could serve as a window into the hidden hearts of Earth, Mars, Venus, and Mercury. As the spacecraft draws closer in the coming years, each transmission will bring us closer to seeing Psyche as it truly is. The images and data it sends back will not only tell us about this single body, but also help us piece together the story of how worlds like our own came to exist. Psyche's metal face may look barren and silent, but beneath it lies a record of cosmic violence. In its scars and its shine, it carries the memory of a time when planets were still being born, a time when the solar system was raw and unsettled. Thorne-Zitkow objects, stars within stars. Most of the time, the life cycles of stars follow patterns that astronomers understand fairly well. Small stars like the Sun end up as white dwarfs. Larger stars explode in supernovas and may leave behind neutron stars or black holes. But sometimes, the process can take a strange and unexpected turn, creating objects that almost seem like they should not exist. One of the strangest ideas ever proposed is that of a Thorne-Zitkow object, a star hiding inside another star. The idea was first suggested in the 1970s by physicists Kip Thorne and Anna Zitkow. They imagined what might happen if a neutron star, one of the densest objects in the universe, somehow ended up inside a red giant, one of the puffiest. Neutron stars are incredibly compact, only about 20 kilometers across, yet containing more mass than the Sun. Red giants, by contrast, can swell to hundreds of times the Sun's size, with a core that is dense but an outer envelope that is so thin it is almost ghostly. If the two objects were brought together, they could form a bizarre hybrid, a neutron star buried deep inside the swollen body of a red giant, like a cosmic Russian doll. How could such a thing happen? The process likely begins with a binary system, two stars orbiting each other. If one of the stars is massive enough, it can explode as a supernova and leave behind a neutron star. If the other star later expands into a red giant, its outer layers might swallow the neutron star whole. Instead of colliding violently and destroying each other, the neutron star could settle into the center of the red giant. There, it would sit at the heart of its partner, quietly consuming material and altering the way the star burns fuel. This idea may sound impossible, but it follows from the rules of gravity and stellar physics. A neutron star, though small, has a powerful gravitational pull. Once inside the red giant's outer envelope, it would sink toward the core, dragging material around it. Normally, a red giant generates energy through nuclear reactions in its core, fusing hydrogen into helium and later fusing heavier elements. But with a neutron star sitting in the middle, the process would change. The neutron star could act almost like an engine, heating the surrounding material and creating unusual conditions for nuclear reactions. Astronomers predict that such an object would look much like an ordinary red supergiant from a distance. To the naked eye or even a telescope, it would just appear as another bright, swollen star. The key differences would be in its chemical fingerprints. The strange conditions inside a Thorne-Zitkow object might lead to the production of unusual elements, ones that are not typically seen in large amounts in other stars. In particular, elements like rubidium, molybdenum, and lithium could be created in greater quantities. By studying the light from a star and breaking it into a spectrum, astronomers could search for these odd chemical signatures as evidence of a hidden neutron star within. For many years, Thorne-Zitkow objects remained purely theoretical. They were fascinating to think about but seemed nearly impossible to confirm. After all, how do you prove that a tiny, invisible neutron star is sitting at the core of a red giant hundreds or thousands of light years away? The best hope was to search for stars with the right chemical oddities. And in 2014, astronomers announced that they had found a candidate. A red supergiant known as HV 2112, located in the Small Magellanic Cloud, showed unusual chemical fingerprints that matched the predictions. While not absolute proof, it was a strong hint that such objects might really exist. The discovery sparked excitement because it suggested that stellar evolution might be more chaotic and varied than previously thought. If Thorne-Zitkow objects are real, they provide a bridge between two very different kinds of stars. They show what can happen when two stellar lives collide and merge, creating something entirely new. They also raise questions about how common such events might be. Binary systems are not rare, and interactions between stars happen often. Could the universe be full of hidden neutron stars lurking inside red giants, masquerading as ordinary supergiants? A neutron star is usually thought of as the final stage of a massive star's life, the leftover after a supernova. But in this scenario, that end is not the end at all. It becomes part of another star's continuing story. Instead of being a corpse, the neutron star becomes a core within a new giant body, altering the way it shines and evolves. It is as if the remains of one star give a second life to another. The physics of a Thorne-Zitkow object is also extreme. Inside the envelope of the red giant, matter would fall toward the neutron star and heat up to astonishing temperatures. The pressure and density could drive reactions that are not seen anywhere else in the universe. This makes such objects not only fascinating curiosities, but also laboratories for testing theories of nuclear physics under exotic conditions. The elements they produce could eventually be spread into space when the star sheds its outer layers, contributing to the cosmic mix of ingredients that future stars and planets will inherit. Yet, despite decades of speculation, proof remains elusive. HV 2112 may be a candidate, but other explanations for its chemical oddities are possible. Astronomers continue to search for more examples, using powerful telescopes and more precise instruments to measure stellar spectra. Each new red giant studied is another chance to find the fingerprints of this hidden process. Astronomy often likes clear divisions: stars, planets, white dwarfs, neutron stars, black holes. But the universe resists neat boxes. It produces strange in-between states, hybrids, and oddities that challenge our understanding. A star with another star inside it is about as strange as it gets, yet it seems entirely possible within the rules of physics. Borisov, a comet from another star system. When the story of Oumuamua was still fresh in the minds of astronomers, another surprise arrived only 2 years later. In August of 2019, a comet was spotted moving through the solar system on a hyperbolic path, a clear sign that it, too, had come from beyond. This new traveler was named Borisov, after Gennady Borisov, the amateur astronomer in Crimea who first identified it. Unlike the mysterious and oddly shaped Oumuamua, Borisov had the familiar appearance of a comet. It carried a glowing head, a halo of gas called a coma, and a long tail trailing behind it, streaming away from the sun. In many ways, it looked like the comets we had always known, but its origin gave it a much deeper significance. For the first time in history, scientists had a chance to study a comet that had formed in another star system. With Oumuamua, the opportunity to observe had been brief and incomplete. There had been no tail, no clear chemical signature, and only a few weeks of data before it slipped into the distance. But Borisov was different. It arrived with a clear display, a tail of gas and dust that stretched thousands of kilometers, and it stayed bright enough for months, giving researchers time to turn powerful telescopes toward it. The gases coming from Borisov included water vapor, carbon monoxide, and traces of other chemicals. These are the same kinds of substances found in comets born in our own solar system. They are often described as the leftovers from the earliest days of planet formation, frozen in deep cold and preserved for billions of years. To see the same materials escaping from Borisov suggested that the building blocks of planets in other systems might not be so different from our own. Across the galaxy, the same basic chemistry seemed to be at work. But there were also differences that set Borisov apart. Observations showed that it was unusually rich in carbon monoxide compared to most comets seen around the Sun. This suggested it may have formed in an especially cold region of its home system, far from its star, where carbon monoxide ice could remain stable. If true, Borisov carried within it the signature of a world very different from ours, where planets and comets formed under much colder conditions. In this way, the comet was more than just a visitor. It was a direct sample of alien chemistry, drifting freely into our reach. Normally, to learn about the chemistry of other star systems, scientists rely on indirect methods such as analyzing the light of distant stars and the faint fingerprints of planets passing in front of them. These techniques can tell us something about atmospheres or surface conditions, but they are limited and uncertain. Borisov was different. It was physical material from another system, shedding its dust and gas right before our eyes. Every photon of light reflected from it carried real information about the world it came from. The Hubble Space Telescope was used to track it, along with some of the largest ground-based telescopes in the world. These observations revealed not only its composition, but also its structure. Borisov's nucleus, the solid heart of the comet, was estimated to be only a few hundred meters across, making it small by comet standards. Yet despite its size, it shone brightly as sunlight vaporized the ices on its surface. The dust and gases it released trailed behind it for millions of kilometers, forming a ghostly tail that stretched across space. In photographs, it looked like one of our own comets, except with the added weight of mystery, because this one had traveled for untold ages from another star. Where had Borisov come from? Its speed and trajectory made it impossible to trace back to a specific star, but computer models suggested it had been traveling for millions, perhaps billions of years, wandering the space between stars. Long ago, some disturbance in its home system, perhaps the gravity of a giant planet or a passing star, had flung it out into interstellar space. From there, it had drifted until chance brought it close enough to our Sun to be seen. In this way, it was like a message in a bottle, thrown into the dark ocean of the galaxy, and only now picked up. Unlike Oumuamua, Borisov did not spark the same debates about artificial origins. Its comet-like appearance and predictable behavior made it clear that it was a natural object. Yet its naturalness was important in its own way. It showed that comets are not unique to our solar system, but may be a common feature of planetary systems everywhere. Just as planets form from disks of dust and gas, so too do comets seem to form, freezing the raw materials of chemistry and carrying them across space. The chemistry Borisov revealed carried implications for the possibility of life. Comets are often seen as carriers of organic molecules, the kinds of carbon-based compounds that form the first steps toward biology. In our own solar system, comets may have delivered these ingredients to Earth billions of years ago, seeding the young planet with the raw materials needed for life to emerge. If Borisov carried similar compounds, as evidence suggested, then other planetary systems might also be rich in the same ingredients. This meant that the seeds of life could be scattered widely across the galaxy, available wherever the right conditions appeared. For months, Borisov was studied intensely. Scientists watched as it drew closer to the Sun, reached its brightest point, and then began to fade as it moved away. In early 2020, something remarkable was observed. The comet's nucleus appeared to fragment, breaking into pieces as the stresses of solar heating pulled it apart. Images showed multiple clumps of material drifting where once there had been a single body. This was not unusual. Many comets in our own system have fractured near the Sun, but it meant even more surface material was exposed, giving another chance to analyze what it was made of. Every observation added to the story, and yet Borisov, like Oumuamua before it, eventually slipped away. By mid-2020, it had become too faint to track. Today, it is still on its outward journey, returning to the emptiness between the stars, carrying with it the chemistry of its home. What remains are the records, the spectra of light, the images, the data that scientists continue to study. Borisov proved that interstellar visitors are not rare flukes. 2 such objects had been seen in just 2 years, suggesting that the galaxy may be filled with countless fragments drifting from system to system. For astronomers, this was a revelation. It meant the space between stars is not empty, but alive with travelers, each carrying a story of its origin. Every one of them is a chance to peer into the history of another world. TRES-2b, the darkest planet in the galaxy. When astronomers first discovered TRES-2b, they quickly realized it was unlike anything they had ever seen before. Most planets reflect some amount of light from their stars, even the gas giants that are thick with dark clouds. But this one was different. TRES-2b was so dark that it seemed to swallow the light around it, reflecting back less than 1% of what struck its surface. To put that in perspective, coal, asphalt, or even black acrylic paint all reflect more light than this planet does. Seen from space, it would appear almost invisible against the darkness of the cosmos, marked only by a faint red glow from its own heat. It is, in many ways, the closest thing to a true shadow world ever found. Part of what makes TRES-2b so strange is that it doesn't fit with what scientists expect from planets that orbit close to their stars. Many so-called hot Jupiters, giant planets that hug their stars tightly, are bright. Their thick, reflective clouds bounce starlight back into space, making them shine with a pearly glow when viewed through telescopes. But TRES 2b, despite being a hot Jupiter itself, defies that rule. Its atmosphere seems to be missing the reflective clouds that give other worlds their brightness. Instead, it contains chemicals that actively absorb light, such as vaporized sodium, potassium, or even titanium oxide. The result is a planet that looks like it has been painted with the darkest black ink in the universe. TRES 2b is not a cold or lifeless place where darkness would be expected. It is incredibly hot, with surface temperatures soaring to over 1,000 degrees Celsius. At that heat, metals would glow red and gases would swirl in violent storms. Yet despite its fiery nature, the planet remains nearly invisible to outside eyes. If you were to somehow stand on the edge of the world, an impossible thought since there is no solid surface, you would see nothing but an endless black sky, even as the burning star above blazed down upon you. The only hint of light would come from the horizon itself, where the planet's superheated gases might glow faintly like smoldering embers. The planet is only about 3 million miles away from its star, far closer than Mercury is to the Sun. This means its day side is constantly blasted with starlight, while its night side bakes in heat that is carried over by high-speed winds. The entire planet is locked in this roasting cycle, with no chance to cool down. Normally, such conditions would produce clouds of bright reflective gas, but somehow TRES 2b resists this. The heat keeps its atmosphere stripped down to light-absorbing chemicals, ensuring it remains forever black. Some scientists suggest it may be in a unique stage of its life, where its atmosphere has lost certain elements, but not yet cooled enough to create new cloud layers. Others think it could be an example of how varied planets in the universe truly are, breaking apart our expectations with every new discovery. The fact that a planet can exist in such extreme conditions, yet still remain invisible against the backdrop of space, shows how much we have yet to learn about the physics and chemistry of alien worlds. For astronomers, TRES 2b is also a challenge in terms of observation. Most exoplanets are studied through the light they reflect or block. When a planet passes in front of its star, we see a tiny dip in brightness, and when it passes behind, we can sometimes measure the reflected light disappearing. But TRES 2b offers almost nothing in return. It is like chasing shadows, trying to pull information from a world that refuses to give itself away. The little we know comes from its faint thermal glow, the whisper of heat that it cannot completely hide. Could there be more planets like this? Could entire systems be filled with invisible giants circling their stars, hiding in the darkness until our instruments grow sensitive enough to find them? If so, the galaxy may hold countless worlds we have yet to see. Future tools may be able to peel back the layers of its atmosphere and detect the exact chemicals responsible for its darkness. They may even discover new forms of matter or unexpected reactions taking place under such extreme heat and pressure. Until then, TRES 2b remains a shadow in the night. Tabby star, the star that keeps dimming mysteriously. When astronomers first noticed Tabby's star, also called KIC 8462852, they were struck by something strange. Its brightness was not steady the way most stars are. Instead, it would suddenly dim by large amounts, sometimes dropping by more than 20% and then return to normal. This was not a small flicker like the kind caused by planets passing in front of stars. It was something far larger, irregular, and unpredictable. It made the star one of the most puzzling objects ever found. The star sits about 1,470 light-years away in the constellation Cygnus. By itself, it is an ordinary F-type star, slightly larger and hotter than the Sun. Nothing about its color or temperature seemed strange at first, but the dimming events changed everything. Normally, when astronomers watch stars for changes in brightness, they are searching for the tiny dips that indicate exoplanets. Those dips are usually very shallow and regular, repeating with each orbit. Tabby's star was completely different. Its brightness would fall at odd times, sometimes for days or weeks, with no pattern at all. When Tabby's star was flagged, scientists at first thought the data might be a mistake, but the dimming was real. Citizen scientists who were helping sift through Kepler data also noticed the unusual behavior. It was unlike anything seen before. This combination of unpredictability and depth in the dimming made the star one of the most famous mysteries in astronomy. One of the first natural explanations was dust. Clouds of dust moving around the star could block its light in uneven ways. Dust has the property of dimming more strongly in blue light than in red, so astronomers looked for color changes during the dips. Indeed, later studies showed that the light did redden slightly during the dimming events, which supported the idea of dust. However, it was still difficult to explain how dust clouds could behave in such a chaotic and long-lasting manner. Another idea was that large groups of comets could be breaking apart near the star. A giant swarm of icy bodies, perhaps disturbed by a passing star, could scatter material into Tabby's system. These fragments might cross in front of the star at random times, causing irregular drops in brightness. This explanation fit some parts of the data, but required an enormous number of comets, far more than we could easily imagine orbiting a single star. There was also the possibility of something much larger and stranger. Some scientists and enthusiasts speculated that the dimming might be caused by artificial structures. If an advanced civilization had built enormous orbiting platforms, or even a Dyson-like megastructure to capture energy from the star, they could block its light in unusual ways. This idea was never the favored explanation among astronomers, but it captured the imagination of the public. It was one of the rare times when the possibility of alien technology was discussed openly in scientific papers, even if only as a far-out hypothesis. Follow-up observations were made with ground-based telescopes and space observatories. Astronomers found that the star did not just dim on short timescales, but its overall brightness seemed to be slowly decreasing over decades. Old photographic plates from the early 20th century showed the star brighter than it is today. If this dimming trend is real, it suggests a much longer process at work. Again, dust was considered the most likely culprit, perhaps from material being blown off from orbiting bodies, or even from the star itself. During some of the dimming events, astronomers could see the chemical fingerprints of dust, supporting that idea further. But not all of the behavior was fully explained. Some dips were very deep, much deeper than a thin veil of dust would normally cause. The mixture of long-term fading and short-term sharp dips made it hard to tie everything together neatly. Most scientists now lean toward dust as the main explanation, possibly from disrupted planets or comets, but many details are still uncertain. What makes it so captivating is that it resists simple answers. Each observation seems to solve part of the puzzle while leaving new questions behind. For the public, the story of Tabby's star shows how science sometimes brushes against the edge of the unknown. The suggestion of alien megastructures was never the leading theory, but it brought attention to the fact that nature can produce signals that mimic what we might expect from advanced life. It was a reminder that if we ever do detect something artificial, it may first look like a strange natural phenomenon we can't explain. Even today, telescopes continue to watch Tabby's star. Amateur astronomers and professional observatories alike keep track of its brightness, waiting for the next big dip. Each event is studied in multiple wavelengths, from visible light to infrared, to gather as much information as possible. Slowly, a picture may emerge that reveals what kind of material surrounds the star and how it moves. Until then, it stands as one of the most fascinating stellar mysteries in our galaxy. Kleopatra, the dog-bone asteroid with moons of its own, floating in the vast darkness between Mars and Jupiter, is one of the strangest objects ever discovered in the asteroid belt. It is named Cleopatra after the famous Egyptian queen, but its shape has earned it a very different nickname, the dog-bone asteroid. When first imaged by powerful telescopes, Cleopatra appeared stretched and narrow, with two bulging ends connected by a thinner middle section. The resemblance to a dog's chew toy was so uncanny that the name stuck. This odd form alone would make it a curiosity, but Cleopatra is even more unusual than it first appears. Circling around it are not one but two tiny moons, companions bound to an asteroid that looks barely stable enough to hold itself together. Kleopatra is huge by asteroid standards. It measures about 270 kilometers from end to end, making it one of the largest bodies in the main asteroid belt. But it is also very light for its size, with a density much lower than solid metal or rock. Scientists believe it is a rubble pile, essentially a collection of broken pieces loosely held together by gravity rather than a single solid body. This helps explain its strange shape. Over billions of years, collisions with other asteroids may have carved away at it, reshaping its body into the long, lumpy form we see today. Instead of being a solid piece of stone, Kleopatra may be more like a pile of debris that just happens to cling together in a dog bone pattern. The two moons orbiting Kleopatra are tiny compared to their parent body, only a few kilometers across, and they were discovered in the early 2000s with the help of advanced imaging techniques. The moons were later named Helios and Selene, after two of Cleopatra's children. Watching these small bodies circle around Kleopatra is like seeing gravity at work on a miniature scale. Despite the asteroid's strange shape and loose structure, its mass is still enough to keep its moons trapped in orbit. This shows how gravity, even when weak, can bind systems together in ways that seem almost improbable. The existence of the moons has also helped scientists learn more about Kleopatra itself. By studying their orbits, astronomers can measure the asteroid's mass and density with far more accuracy than by observation alone. These calculations confirmed that Kleopatra is far less dense than it should be if it were solid metal. Instead, it appears to be made mostly of metal-rich rubble, perhaps remnants of a larger body shattered long ago. Some researchers even think Kleopatra's moons might have been created from material ejected from the asteroid itself, thrown into space by collisions, and later captured into orbit. Kleopatra's twin lobes and narrow neck seem fragile, as though a sharp nudge might break the asteroid into two separate pieces. Yet it has held together for billions of years, spinning through space while its tiny moons follow close behind. Not all celestial bodies conform to neat spherical shapes. In fact, most asteroids are irregular, scarred and misshapen by countless impacts. Kleopatra just happens to be one of the most dramatic examples, stretched to the point of looking artificial, even though it is entirely natural. It doesn't have the smooth plains of a planet or the sharp peaks of a mountain range, but instead appears mottled and uneven, with ridges and craters scattered across its length. Light reflects differently from each region, suggesting patches of varying composition. Its metallic nature, likely dominated by nickel and iron, gives it a brightness that sets it apart from the darker, carbon-rich asteroids nearby. Yet this metallic body is not solid iron like the core of a planet. It is porous, with large empty spaces between chunks of material, as if the asteroid were built from scraps. One of the mysteries surrounding Kleopatra is how it formed its distinctive shape. Some scientists suggest that its rapid rotation may have stretched it out over time. If the asteroid was spinning fast enough, centrifugal force could pull it into an elongated form, especially if it were already a loose rubble pile. Others propose that repeated collisions chipped away at its structure, carving out its narrow waist and leaving behind the dog-bone form. Whatever the case, its survival shows that even fragile-seeming shapes can remain stable for immense spans of time when held together by gravity's patient hand. The presence of moons orbiting such a bizarrely shaped body also challenges ideas about orbital dynamics. Normally, small moons orbiting irregular objects would be expected to face unstable paths, tugged unpredictably by uneven gravitational pulls. Yet Helios and Selene follow orbits that appear remarkably steady. This stability has helped astronomers refine their models of how gravity works around non-spherical bodies. It also raises the possibility that moons may be more common around large asteroids than once thought. If even a dog-bone-shaped rubble pile can keep companions, then many other asteroids may do the same. By examining its shape, rotation, and moons, Researchers gain insight into how collisions and breakups sculpt the rocky debris left over from planet formation. Kleopatra may also help explain how binary asteroids, systems with two major bodies orbiting each other, come into existence. Its narrow neck suggests it could even represent a transitional form, a single body that might one day split into two separate asteroids if its rotation increases further or another collision delivers the final blow. In recent years, more detailed studies have been made possible by powerful observatories like the Very Large Telescope in Chile. These instruments captured sharper images of Kleopatra, confirming its dog-bone outline with far greater clarity than before. They also traced the paths of its moons in detail, allowing for improved measurements of its density and confirming its rubble pile nature. Imagining standing on Kleopatra is as surreal as picturing a landscape on Psyche. Its surface gravity is weak, only a fraction of what we experience on Earth, and the ground beneath would not be solid in the usual sense, but more like a loosely packed field of metallic boulders. The horizon would curve oddly, given its elongated shape, and the sight of its moons drifting above would give the scene an eerie beauty. Its existence shows how diverse asteroids can be, and how, even in the strangest corners of space, gravity finds a way to bring order, holding moons in orbit around a body that looks like it should barely hold itself together. Ton 618, one of the largest black holes ever measured. Black holes themselves are already strange, bending space and time, swallowing matter and hiding everything behind an invisible boundary called the event horizon. But Ton 618 takes this strangeness to an entirely new level. With a mass greater than 40 billion suns, it is a cosmic giant, an object whose size and power are difficult for the human mind to truly grasp. Ton 618 was first noticed not as a black hole, but as a quasar, a brilliant, distant beacon of light shining from billions of light years away. Quasars are powered by supermassive black holes at the centers of galaxies. As matter falls toward these black holes, it heats up and glows, releasing energy that can outshine entire galaxies. The light from Ton 618's quasar has traveled for more than 10 billion years to reach us, meaning we see it as it was when the universe was less than a third of its current age. Even across such a gulf of space and time, its glow is unmistakable, a sign of just how powerful this object is. When astronomers studied Ton 618 in detail, they realized that the quasar's light was so bright that only a black hole of unimaginable size could explain it. By analyzing the light, they estimated the mass of the central black hole, and the number was staggering, over 40 billion times the mass of the Sun. That makes it one of the largest black holes ever measured. Its event horizon, the point of no return, would be so large that it could swallow our entire solar system, including the Sun, the planets, and far beyond, with room to spare. If placed at the center of our galaxy, it would dominate the night sky. To put it into perspective, the supermassive black hole at the center of our own Milky Way, Sagittarius A star, is massive in its own right, weighing about 4 million suns. Yet compared to Ton 618, it is tiny. Ton 618 is more than 10,000 times heavier, a true monster among monsters. Even other famous black holes, such as the one in the galaxy M87, which was the first ever imaged directly, are smaller in comparison. This makes Ton 618 an outlier, a cosmic heavyweight that forces astronomers to rethink how such giants can form and grow. The sheer scale of Ton 618 raises questions about the limits of black hole growth. Black holes form from the collapse of massive stars, but those early seeds are far smaller than Ton 618. To reach such an enormous size, a black hole must consume matter at a furious pace, swallowing stars, gas, and perhaps even other black holes. Some theories suggest that black holes in the early universe had a head start, forming directly from giant clouds of collapsing gas without going through the star stage first. Others think that black holes grow in bursts, feeding on enormous streams of matter when galaxies collide. Ton 618, with its staggering size, may be the product of both pathways. A black hole that formed early and grew relentlessly over billions of years. The light we see from Ton 618 comes from the matter falling into it, forming an accretion disk. This disk of gas swirls at incredible speeds, heating up to millions of degrees and blasting out radiation across the universe. That energy travels through intergalactic space and eventually reaches Earth as the brilliant quasar light. What is remarkable is that the quasar is so bright that it outshines not just its host galaxy, but entire clusters of galaxies. For astronomers studying the distant universe, quasars like Ton 618 serve as beacons, shining across the dark and allowing us to glimpse the cosmos as it was in ancient times. Its gravity shapes not only its immediate surroundings, but also the larger galactic environment. The jets and winds from quasars like Ton 618 can affect star formation in their galaxies, heating gas and pushing material away. In this sense, black holes are not just destroyers, but also sculptors, influencing how galaxies live and grow. Astronomers are still trying to understand how rare such giants are. Are there many black holes as large as Ton 618 scattered across the universe, hidden in the depths of space? Or is it one of a small handful of ultramassive black holes that formed under special conditions? Each discovery of a quasar gives more clues, but so far, Ton 618 remains one of the most extreme examples ever measured. Its size alone makes it a landmark in our exploration of the cosmos. Objects like this remind us how small we truly are in the grand scale of the universe. Here on Earth, the Sun seems immense, a blazing sphere that dominates our sky. But in the shadow of Ton 618, even the Sun is reduced to insignificance. This black hole has the mass of tens of billions of suns. Its event horizon could easily engulf our entire star and countless others in a single swallow. It is a reminder that the cosmos is filled with extremes far beyond the limits of human experience. And yet, even Ton 618 has its boundaries. As immense as it is still finite, still a part of the universe's fabric. Ton 618 is just one of the bright examples of nature's creativity. A supermassive black hole that stands as one of the largest cosmic structures shaped by gravity alone. Astronomers expect to find even more extreme black holes lurking at the edges of the observable universe. Some may even far surpass Ton 618 in size. Each one discovered will not just be a number on a chart, but a window into the deep past of the universe, when the first galaxies were forming and the first giants were being born. Until then, Ton 618 remains one of the most staggering discoveries in astronomy. HD 189733b, the planet where it rains glass sideways. HD 189733b orbits a star about 64 light-years away in the constellation of Vulpecula, making it relatively close in astronomical terms. Even though it cannot be visited, astronomers have studied its atmosphere in surprising detail. What they found paints a picture of a world that seems ripped out of a nightmare. A gas giant where winds roar at thousands of kilometers per hour, and where rain is made not of water, but of glass-like particles. HD 189733b's orbit takes just over 2 Earth days. Because of that, its atmosphere is blasted with radiation and heat. The temperatures climb to around 1000 degrees Celsius. That heat, combined with the chemistry of the atmosphere, creates bizarre conditions that push the limits of what we think of as weather. Just like our moon always shows one face to Earth, HD 189733b always shows one face to its star. One side of the planet is in eternal daylight, constantly baked by radiation. The other side is in endless night. This imbalance sets up enormous forces in the atmosphere. Heat tries to move from the bright side to the dark side, while the cold regions push back, and the result is wind unlike anything on Earth. These winds can whip around the planet at speeds of up to 7,000 kilometers per hour, fast enough to circle the Earth in less than half an hour. But the wind is only part of the nightmare. What makes HD 189733b truly terrifying is what's carried in those winds. Observations suggest that tiny particles of silicate, materials that form glass on Earth, are suspended in its atmosphere. In the searing heat of the day side, these particles can condense into clouds. On the cooler side, they fall as rain. Except this isn't rain as we know it. Imagine shards of glass carried sideways at hypersonic speeds, cutting across the sky. On this planet, the very air would shred anything that tried to exist within it. From space, the planet even looks dangerous. It has a striking deep blue color, not unlike Earth when viewed from afar. At first glance, you might think of oceans, calm skies, and a world that could support life. But that blue is not water. It's the signature of scattered light in its atmosphere, enhanced by the glass particles and the chemicals within. It is a false promise, a deadly disguise. Beneath that serene appearance lies an incredibly hostile environment. When the planet passes in front of its star, some of the starlight filters through the planet's atmosphere. By studying these fingerprints, scientists have revealed the presence of silicates and molecules that suggested violent weather patterns. The deep blue color was detected through measurements of how the planet reflected light. Piece by piece, the portrait of a glass-raining, storm-ravaged giant came together. The sheer scale of this weather is staggering. On Earth, the strongest winds in hurricanes may reach a few hundred kilometers per hour. Those are enough to tear apart buildings and reshape coastlines. On HD 189733b, winds reach speeds dozens of times higher. The sideways glass rain adds another dimension of destruction. Nothing solid could stand in such an environment. Earth's climate is shaped by sunlight, oceans, and air. On gas giants like Jupiter, storms like the Great Red Spot can rage for centuries. But HD 189733b shows that conditions can be pushed into truly alien territory. Despite its violence, the planet has become one of the most studied exoplanets in the universe. Its relatively close distance to Earth and the brightness of its star make it easier to observe than many others. Each new telescope that turns toward it adds another detail to the puzzle. The James Webb Space Telescope, for example, has been tasked with looking deeper into its atmosphere, hoping to unravel the layers of chemistry that make it such a hostile place. How long can a world like this last, being battered by its star and shedding parts of its atmosphere into space? Some models suggest that hot Jupiters may gradually lose mass over time, slowly evaporating under the intense radiation. They might eventually shrink down to smaller rocky cores, leaving behind relics of their former size. In this way, HD 189733b could be part of a longer evolutionary story, a snapshot of a planet in transition. It is one thing to read about winds or temperatures in numbers. It is another to picture yourself on the edge of this world, watching blue clouds streak by, feeling the pull of gravity beneath alien skies. The idea of rain made of glass is vivid in a way that few scientific discoveries are. It makes the universe feel more strange and more alive than a simple catalogue of planets ever could. It shows that other worlds are not just variations of Earth. They are realms with their own rules, their own nightmares, and their own impossible beauty. HD 189733b will continue to be a key target for study because it teaches us the extremes of what a planet can be. It is one planet among billions, yet its storms of sideways glass stand as one of the clearest examples that the universe is not bound by our expectations. It builds worlds that are not only strange, but almost unthinkable. Worlds that remind us how much there still is to discover. Magnetars, the most magnetic objects in the cosmos. Magnetars are the most magnetic things ever discovered. They are a special type of neutron star, themselves already among the most extreme objects in existence. A magnetar is born when the collapse of a massive star produces a neutron star that spins extremely fast and winds up its magnetic field to extraordinary levels. The result is a magnetic field up to 1 trillion times stronger than Earth's, so strong that it can twist atoms, distort space around it, and unleash energies that are hard to fully imagine. The sheer strength of these magnetic fields makes them unlike anything else in nature. Even at a distance of thousands of kilometers, their influence is enough to change the behavior of matter and radiation. One of the most dramatic things magnetars do is release sudden outbursts called starquakes. Their crusts, made of dense matter, are under incredible stress from the immense magnetic forces. When the crust cracks, it can release a burst of X-rays and gamma rays that shines across the galaxy. These bursts are so powerful that on rare occasions they have been detected from magnetars tens of thousands of light-years away. In 2004, one such flare came from a magnetar known as SGR 180620. The explosion was so intense that it briefly disturbed Earth's ionosphere and affected satellites, even though the magnetar was on the far side of the galaxy. The energy released in just a fraction of a second was more than the Sun emits in 100,000 years. To put the power of these objects into perspective, consider that Earth's magnetic field protects us from the solar wind and guides compass needles. It is strong enough to shape the environment around our planet. A magnetar's field, however, is so much stronger that if one were as close as the Moon, it could erase the magnetic strips on every credit card on Earth. At even closer ranges, it would disrupt the very structure of atoms, pulling electrons away from their nuclei. Physics as we know it breaks down in such conditions, which is why magnetars remain one of the most mysterious laboratories in the cosmos. Despite their incredible power, magnetars are relatively short-lived. Their extreme magnetic fields drain energy rapidly, causing them to spin down and fade over a period of only about 10,000 years. This is a blink of an eye in cosmic time. Most neutron stars live much longer, slowly cooling and spinning down over millions of years. But magnetars burn out fast. This makes them rare. Astronomers estimate that only a handful exist in our galaxy at any given time. Out of the billions of stars in the Milky Way, only around 30 magnetars have been identified so far. Each one is a precious window into this violent and extreme branch of astrophysics. Some of their flares are so strong that they can be mistaken for short gamma-ray bursts, which are usually caused by merging neutron stars or other catastrophic events. In fact, the discovery of magnetars helped explain some mysterious signals seen by satellites in the late 20th century. Before then, astronomers wondered what could possibly produce such sudden, powerful flashes of high-energy radiation. Magnetars turned out to be the answer for many of them, showing that these compact stars could outshine entire galaxies for brief moments of time. Some researchers think they might be connected to the enigmatic fast radio bursts, or FRBs, that have puzzled astronomers for years. FRBs are extremely bright flashes of radio waves that last only milliseconds but come from billions of light-years away. In 2020, a magnetar in our own galaxy, SGR 1935 plus 2154, produced a burst of radio waves at the same time as an X-ray flare, strongly suggesting that at least some FRBs come from magnetars. If this connection holds true, it means these stars are also key players in one of the most exciting new areas of astronomy. Studying magnetars is difficult because of their rarity and unpredictability. They spend much of their time relatively quiet, then suddenly unleash a storm of energy without warning. Observatories that scan the sky for X-rays and gamma rays are constantly on the lookout for these events. When a flare does happen, telescopes across the world and in orbit rush to observe it before it fades. Each outburst provides clues about the internal structure of these stars, the nature of ultra-strong magnetic fields, and the processes that trigger such incredible explosions. The existence of magnetars also forces scientists to think about the limits of matter. Neutron stars already represent matter crushed beyond anything we can create on Earth, where protons and electrons are squeezed together to form neutrons. In magnetars, the magnetic fields are so strong that they may create conditions never seen anywhere else. Theories suggest that exotic particles or new forms of matter could exist inside them. These possibilities make magnetars not only astrophysical objects, but also places for testing fundamental physics in ways no human experiment could. What is remarkable is how something so small can have such a huge impact. A magnetar is tiny compared to a star, smaller than a city in diameter, yet it can outshine a galaxy during one of its bursts. Its field lines stretch far into space, shaping its surroundings on scales far larger than its size. This combination of compactness and raw energy makes magnetars among the most extreme examples of how the universe pushes boundaries. What would happen if a magnetar were closer to us? Luckily, none are near enough to pose any threat, but imagining their effects makes clear how dangerous they would be. A burst from a magnetar within a few dozen light-years could strip away Earth's atmosphere and make the planet uninhabitable. Thankfully, the ones we know of are safely distant, allowing us to study them without fear. Arrokoth, the snowman-shaped relic of the early solar system. When the New Horizons spacecraft made its historic flyby of Pluto in 2015, it did not stop there. Its journey continued deeper into the Kuiper Belt. In January 2019, the spacecraft approached another target, one far smaller than Pluto. This object was first known as 2014 MU69, then nicknamed Ultima Thule, and later officially named Arrokoth. Arrokoth is a small, fragile body drifting in the cold darkness more than 4 billion miles away from Earth. Measuring just about 36 kilometers across, it looks like two round objects pressed together. One lobe is larger and flatter, while the other is smaller and rounder. The two are fused at a narrow neck, giving Arrokoth its distinct snowman-like appearance. The way it looks is not just charming, it is also incredibly important, because it tells us how the very first building blocks of planets may have come together. Unlike planets and moons that have been battered by geological activity, volcanoes or atmospheres, Arrokoth has remained untouched for billions of years. It lies in a region of the solar system where things move slowly, where collisions are rare, and where temperatures are unimaginably cold. In this frozen, distant environment, Arrokoth has been preserved almost exactly as it was when the solar system was young. Scientists believe it is a leftover piece from the time before planets were fully formed. Many objects in space are lumpy, irregular, or potato-shaped, but Arrokoth is clearly made of two bodies that once orbited each other before gently merging. This kind of object is called a contact binary. The two lobes likely formed separately from the same cloud of dust and ice and then drifted together at very low speed, sticking to each other rather than smashing apart. This is an important detail because it suggests that planet formation was not always violent and catastrophic. Instead, at least in some cases, it was a slow, quiet process of pieces coming together like puzzle parts, settling into stable shapes over time. The surface of Arrokoth is smooth compared to many asteroids and comets. There are fewer large craters than expected, which again shows that it has not been hit by many objects since its formation. The reddish color of its surface comes from complex organic molecules formed by radiation breaking apart simple compounds like methane and water ice. These molecules, called tholins, are common in the outer solar system and may have played a role in the chemistry that led to life on Earth. The Kuiper Belt, where Arrokoth resides, is filled with countless similar objects. Some are larger, like Pluto and Eris, while others are small and faint, difficult to detect from Earth. Most of them are leftovers, material that never gathered into a planet. By studying Arrokoth, scientists can learn not only about one peculiar snowman-shaped body, but about the entire population of primordial building blocks. Each one is a clue to how dust and gas once swirled in the solar system's disk, clumping together and setting the stage for the birth of planets. What makes Arrokoth particularly valuable is that it is far less disturbed than objects closer to the Sun. Asteroids in the main belt, for example, have been baked by heat, fractured by impacts, and sometimes tugged apart by planetary gravity. Comets, when they enter the inner solar system, lose their icy material in spectacular displays. Arrokoth has remained in its cold, quiet orbit for over 4 billion years. Its very existence shows us what the original solar system pieces might have looked like before being altered by time and activity. For New Horizons, flying by Arrokoth was a feat of precision and planning. The spacecraft traveled more than 1 billion miles beyond Pluto to reach its target. Arrokoth itself is incredibly small and faint, making it difficult to track. Yet in January 2019, the spacecraft passed within just 3,500 kilometers of the object, snapping detailed pictures and measuring its composition. This was the most distant flyby ever attempted, and it turned out to be one of the most revealing. For the first time, humanity got a close look at one of the original building blocks of planets. For years, scientists thought the early solar system was a chaotic place where planetesimals, small bodies like Arrokoth, smashed into each other at high speeds, shattering into fragments before slowly reassembling. But Arrokoth's gentle contact binary structure suggests otherwise. Its lobes came together at just a few meters per second, about the speed of a slow walk. This hints that at least in the Kuiper belt, and perhaps more broadly, objects grew by peaceful mergers, not violent crashes. If true, this changes how we picture the steps that built planets like Earth. Arrokoth's name comes from the Powhatan Algonquian word for sky, chosen to honor Native American heritage. This name reflects both the deep past of our solar system and the human effort to connect science with culture. Just as Arrokoth is a bridge to the beginning of the solar system, its name is a bridge between modern discovery and ancient ways of seeing the sky. As New Horizons continues its journey through the Kuiper belt, Arrokoth remains a symbol of what lies beyond our familiar planets. Its snowman shape may seem almost playful, but it is also profoundly important. The more we study objects like Arrokoth, the clearer it becomes that the solar system is a place of incredible diversity. From giant planets to tiny relics, from active comets to frozen time capsules, every object has a role in telling the story of how our cosmic neighborhood was built. The black hole that launched a jet across a galaxy. Black holes are not just silent consumers. Under the right conditions, they can become engines of unimaginable power, releasing streams of matter and energy across cosmic distances. These streams, called jets, are some of the most striking features in the universe, visible across millions of light years. One black hole in particular has produced a jet so large that it stretches farther than the galaxy it comes from. When gas, dust, or even entire stars fall toward a black hole, this material swirls into a disk around the black hole, heating up to extreme temperatures. The swirling gas produces intense magnetic fields, and those fields can twist and channel some of the material away from the black hole's grasp. Rather than being consumed, this matter is flung outward at nearly the speed of light, forming a narrow jet that cuts through space. These jets often extend far beyond the galaxy itself, shining brightly in radio waves and other forms of radiation. The black hole responsible for one of the largest known jets is located in the galaxy Pictor A, about 500 million light-years away. Its jet is so vast that it spans over 1 million light-years in length, longer than the Milky Way galaxy itself. This means that while the black hole itself is only a few dozen kilometers across, the structure it produces dwarfs entire clusters of galaxies. The sheer imbalance between the tiny size of the black hole and the enormous scale of the jet it powers is almost absurd, a reminder of how extreme physics becomes under these conditions. Observing such jets is not simple. They are not usually visible in regular light. Instead, astronomers use radio telescopes, X-ray detectors, and other instruments that can reveal the energy they release. The jet in Pictor A, for example, has been studied extensively in radio waves, showing a long, thin structure that glows across intergalactic space. The Chandra X-ray Observatory has also imaged it, revealing hotspots along its length where particles collide with surrounding gas, releasing bursts of radiation. Each of these hotspots marks a point where the jet slams into intergalactic material, creating shocks similar to sonic booms, but on a cosmic scale. What makes these jets so puzzling is how organized they remain over such distances. Imagine a fire hose shooting water for millions of miles without breaking apart or losing focus. That's essentially what these black hole jets are doing. The stability is thought to come from strong magnetic fields, which guide the particles into a tight stream. But exactly how the fields are generated and maintained remains an open question. The physics at play involves a combination of relativity, plasma behavior, and magnetic interactions that push the limits of current understanding. The energy output of these jets is staggering. In many cases, they carry more energy than all the stars in the galaxy combined. For galaxies like Pictor A, the jets actively shape their surroundings. As the jet plows through intergalactic gas, it heats and stirs the material, affecting how new stars form. This role of black holes as galactic architects is a relatively recent discovery. For a long time, black holes were thought to be passive endpoints of massive stars, objects that did little more than swallow matter. But observations of jets have shown that they can influence their entire cosmic neighborhoods. Without these jets, galaxies might look very different, with different numbers of stars, different shapes, and perhaps even different chances for life to arise. The jet in Pictor A is just one example of this larger story, a vivid reminder that black holes are active participants in cosmic evolution. A galaxy is already an enormous thing, containing billions of stars across tens of thousands of light years. But a jet, like the one in Pictor A, stretches far beyond that, crossing the space between galaxies. To put it into perspective, if such a jet started at the center of the Milky Way, it would extend well beyond the Andromeda Galaxy, our nearest large neighbor. It is not just a galactic feature, it is an intergalactic one, connecting different realms of the universe with streams of high-energy matter. One might wonder what it would look like if Earth were closer to such a jet. The truth is, life here could not survive the radiation. Jets release torrents of energetic particles that would strip away atmospheres and sterilize planets in their path. Thankfully, our galaxy's central black hole, Sagittarius A star, is relatively quiet. It is not currently launching such massive jets, though there is evidence it may have in the distant past. For civilizations elsewhere, however, living near an active jet would mean existing under constant exposure to cosmic rays and radiation on levels far beyond what we experience from the Sun. The mystery of these jets is far from solved. Even though astronomers can see them, measure their lengths and study their radiation, the exact process by which black holes launch them is still debated. How does material that should be falling inward instead get accelerated outward at nearly the speed of light? How do magnetic fields remain so stable across such vast distances? These questions lie at the frontier of astrophysics. Hyperion, the sponge-like moon of Saturn. Among the many strange moons orbiting Saturn, one stands out for looking less like a world and more like something that might sit in a kitchen sink. This is Hyperion, a moon that resembles a giant sponge drifting through space. Where most moons show smooth plains, ridges or craters with familiar rounded shapes, Hyperion's surface is filled with deep, sharp-edged holes that make it look hollowed and fragile. Hyperion is not large compared to Saturn's biggest moons. It is about 270 kilometers across, small enough that its gravity is weak and its shape irregular. Instead of being a neat sphere like many larger moons, it has a lumpy, potato-like form. That irregularity alone sets it apart, but what truly defines Hyperion is its porous nature. Studies suggest that up to 40% of its volume may be empty space, making it more like a cosmic sponge than a solid rock. The material that makes up Hyperion is thought to be a mixture of ice and rock, but because it is packed so loosely, it doesn't compact under its own weight. Instead, the moon is lightweight and fragile, almost as if it could crumble apart if struck hard enough. Unlike the round, shallow craters seen on other moons, Hyperions are deep and sharp, often with dark material settled at the bottom. When an object hits Hyperion, instead of compressing the surface and spreading out energy, the impact tends to punch straight down, digging narrow pits into the porous body. The loose, sponge-like interior absorbs the shock, preventing the craters from collapsing into broader basins. The result is a landscape unlike anywhere else in the solar system, a honeycomb of pits, each one a mark of countless impacts over time. From orbit, it looks carved and eroded, But this texture comes not from weather or erosion, but from its unique structure and the violence of space. When the Cassini spacecraft flew by Hyperion in 2005, it gave us our closest and most detailed view. The images confirmed just how strange this moon really is. The craters had strange shadows, making the moon appear jagged and rough. Some pits seemed to contain reddish material thought to be hydrocarbons. These organic materials hint at the raw chemistry that pervades the outer solar system, scattered across moons, comets, and even asteroids. Most moons, even irregular ones, eventually settle into a predictable rotation, with one face locked toward their planet, much like our moon. Hyperion defies this rule. Instead of spinning steadily, it tumbles chaotically through space. Its rotation is so unstable that it cannot be predicted far into the future. The combination of its odd shape, weak gravity, and the gravitational tug of Saturn and its larger moons keeps Hyperion from locking into a simple rhythm. This makes it one of the only known moons with a completely chaotic rotation. If you were standing on its surface, the Sun and Saturn would not rise and set in any regular pattern. Instead, the sky would spin unpredictably, with days and nights impossible to measure. The cause of this chaotic tumbling comes down to physics. Hyperion's irregular shape means that different parts of it feel different pulls from Saturn's gravity. Unlike a smooth, round moon, there is no stable way for it to balance. Larger moons, with their stronger self-gravity, smooth themselves out and lock into steady orbits and spins. But Hyperion, small and lumpy, simply can't. Every time it orbits Saturn, tiny variations in the gravitational pull twist it differently. Over time, these small shifts add up, throwing it into a tumble that never settles. Mathematically, this makes Hyperion a fascinating example of chaos in the natural world, a body whose motion can be described but not predicted with certainty far into the future. Its porous body suggests it may be a remnant from the early solar system, a piece that never coalesced into something larger. If it had formed closer to Saturn, the planet's stronger gravitational forces might have pulled it apart. But in its current orbit, it has survived, quietly circling Saturn while carrying its sponge-like body through billions of years of history. Saturn's larger moons, Triton with its thick atmosphere, or Enceladus with its smooth ice and geysers, have surfaces that suggest worlds of their own, with processes shaping them from the inside. Hyperion, by contrast, looks almost untouched, as if it has no internal activity at all. It does not smooth over its scars or resurface itself. Instead, it has remained an open record of impacts and cosmic weathering, with each new crater adding to its jagged appearance. The way Hyperion absorbs impacts raises questions about how such bodies hold together. If nearly half its volume is empty space, then how do the collisions that carved its craters not simply shatter it apart? One idea is that the impacts compress the porous material locally without transmitting force across the entire body. In other words, Hyperion acts like a shock absorber, its sponge-like makeup preventing destruction by soaking up energy. That same property may explain why its craters are so deep and sharp-edged. They are not erased by collapse, but preserved by the weak structure around them. In this way, Hyperion has managed to stay intact, despite being so fragile in theory. With gravity so weak, walking or even standing would be nearly impossible. You might float off the surface with a single jump. The sky would offer no comfort either, as Saturn and the Sun would whirl unpredictably due to the tumbling rotation. It would be a landscape where nothing feels steady, a place that embodies the strangeness and instability of the outer solar system. The Boomerang Nebula, the coldest known place in the universe. One might think that nothing could be colder than the natural background left over from the Big Bang. This faint glow, known as the cosmic microwave background, fills the entire universe at a temperature just a few degrees above absolute zero. It sets what seems like a natural floor for how cold things can get in the vast darkness between stars and galaxies. Yet astronomers discovered a place even colder than the background of space itself. This is the Boomerang Nebula. a cosmic oddity that defies expectations, and shows how the rules of physics can create extreme conditions in ways we rarely see elsewhere. The Boomerang Nebula is a cloud of gas located about 5,000 light-years away in the constellation Centaurus. At first glance, it looks like many other nebulae, faint and ghostly, shaped by material flowing away from a dying star. But when scientists measured its temperature, they found that the gas in the nebula is only about 1 degree above absolute zero, making it the coldest known natural place in the universe. Even the microwave background, or CMB, which should bathe everything evenly, is warmer than this strange cloud. Somehow, this patch of the cosmos has managed to dip below the temperature of space itself. The secret lies in the way the gas is moving. The star at the center of the Boomerang Nebula is in its final stages of life. Like many aging stars, it is shedding its outer layers, throwing material outward in a powerful stellar wind. In the case of the Boomerang Nebula, this wind is flowing out at an incredible speed, over 150,000 kilometers per hour. As the gas streams outward, it expands very quickly, and this rapid expansion cools it down, much like the way air from a spray can feels cold when it is released. On Earth, we see similar physics in action when compressed gas escapes and chills its surroundings. But here, it is happening on a scale measured in trillions of kilometers. The result is a vast expanding shell of material that has reached extremely low temperatures. Astronomers first noticed this extreme chill in the 1990s when they observed the nebula with radio telescopes. Later, the Hubble Space Telescope captured striking images that revealed its structure. The name Boomerang came from early ground-based observations that showed a lopsided, bow tie-like shape. In truth, the nebula looks more like a giant hourglass, with 2 lobes of gas flowing away from the central star. The symmetry of these outflows suggests that something in the star's dying process shaped the material into this form, perhaps even a companion star, orbiting nearby that helped focus the flow. The coldness of the Boomerang Nebula is not permanent. Over time, as the gas continues to spread and thin, it will eventually warm back up to the background temperature of space. This makes the nebula temporary, a fleeting stage in the long death of a star. Eventually, the central star will collapse further, likely becoming a white dwarf, and the nebula will fade as its material mixes back into the galaxy. But for now, it stands as a snapshot of a very particular moment in cosmic history, when stellar winds and expansion created the coldest known environment anywhere. Some stars explode in supernovas, scattering heavy elements across space. Others fade more gently, peeling away their outer layers to form planetary nebulae, glowing shells lit by the dying core within. The Boomerang Nebula belongs to this second category, but it shows an extreme version of the process. The rate at which it is losing mass and the speed of its winds are unusually high, and this rapid outflow is what allows the extraordinary cooling to occur. For scientists, studying this nebula highlights how space is not always static and still, but shaped by the forces of motion and pressure. The fact that something can cool below the CMB might seem impossible, yet the laws of thermodynamics allow it when expansion outpaces the heating influence of the background radiation. On Earth, we think of cold in terms of winter nights, icy winds, or liquid nitrogen experiments. But the chill of this nebula is on a scale far beyond anything we could create naturally here. Absolute zero is the point at which all atomic motion stops, and the Boomerang Nebula is only a fraction of a degree above that. If a human could somehow stand within it, which of course is impossible, heat would leave their body not through contact, as in earthly cold, but through the sheer emptiness around them, where atoms themselves barely move. It is a coldness that is more about the absence of activity than the sensation we associate with ice. Not every cosmic wonder is violent and explosive. Some are subtle, shaped by the gentle but relentless physics of expansion and cooling. A dying star, shedding its skin into space, has managed to create a pocket of the coldest known matter in the universe. J. 1407b. the exoplanet with Saturn-like rings, but 200 times bigger. When astronomers first noticed the strange dips in the brightness of a young star called J1407, they knew they were looking at something unusual. The light didn't fade in a simple, predictable way, like when a planet crosses in front of its star. Instead, it dimmed and brightened in complex patterns, almost as if the star had been wrapped in moving shadows. After studying the data more closely, scientists realized the explanation. A giant planet, now known as J1407b, was surrounded by a massive system of rings. Not just rings like Saturn's, but rings that were on a completely different scale. The sheer size of these rings is hard to picture. Saturn's rings, as wide and stunning as they are, span about 175,000 miles across. That's already enough to make them one of the most breathtaking sights in our solar system. But J1407b's rings are thought to be 200 times larger. If Saturn had rings of that scale, they would stretch across the sky of Earth, brighter and more dramatic than even the full moon. Looking up at night, the rings would dominate the heavens, their arcs spanning from horizon to horizon. For any beings living on a moon around J1407b, the sky would never be empty. It would be filled with dazzling bands of light and shadow. J1407b itself is a giant planet, far larger than Jupiter. Some estimates place its mass at more than 10 times that of Jupiter, making it a possible super-Jupiter, or even something that blurs the line between planet and brown dwarf, the failed stars that never ignite. Such a huge world has the gravity to hold on to an enormous ring system. These rings are not just decorative, they are the raw material of moons. Within the swirling bands, clumps of dust and ice may already be coming together to form satellites, just as scientists think happened in the early solar system when Saturn's moons were born. Astronomers didn't actually see the rings directly. Instead, they studied how the light of the star J1407 dimmed over time. The patterns of dimming suggested that the starlight was being blocked by something complex. Not just a solid planet, but a whole system of rings with gaps and divisions. It was like watching a shadow play in the sky and piecing together the shape of what passed in front. This technique, though indirect, revealed one of the largest and most detailed planetary structures ever discovered. In our solar system, Saturn's rings are unique. Jupiter, Uranus and Neptune all have rings, but they are faint and barely visible. Saturn is the only planet whose rings are broad and bright enough to catch the eye. But J1407b suggests that in other systems, giant rings may be far more common. If so, then what we see around Saturn may just be a small example of something much larger and more dramatic that nature is capable of creating. Saturn's rings may eventually fade, as dust and ice drift away or fall into the planet. J1407b's massive rings might also be temporary, lasting only a few million years before forming moons or dispersing. That means we may be catching this planet at a rare moment in its history, during a phase that won't last forever. If humanity ever had the chance to send a spacecraft to J1407b, the view would be unlike anything. A probe orbiting near the planet would be surrounded by countless bands of rock and ice, each circling at different speeds, stretching out for tens of millions of miles. The light from the distant star would cast long shadows across the rings, making them glow like enormous ribbons of silver. It would be a sight so grand that even the most detailed art would struggle to capture it. The rings of J1407b are not only wide, but detailed. Observations suggest they have many gaps, much like Saturn's rings. These gaps may be caused by moons forming inside the rings, sweeping up material as they orbit. If true, then J1407b may already be home to dozens of moons in the making, some perhaps as large as Earth's moon. Astronomers are eager to learn more about J1407b, but the challenge is that it is very far away, about 420 light-years from Earth. That distance makes detailed study difficult. For now, we can only observe the planet when it passes in front of its star, an event that does not happen often. But even with these limited glimpses, J1407b has already shown us that nature is capable of building structures on a scale that dwarfs anything in our neighborhood of the cosmos. What else might be waiting out there, hidden in the light of distant stars, waiting for us to notice the strange shadows they cast? Apophis, the asteroid that terrified Earth scientists. In 2004, a small team of astronomers scanning the skies for near-Earth objects picked up something faint, moving against the background stars, and on first calculation, its orbit looked uncomfortably close to Earth's. This object was later named Apophis, after the Egyptian god of chaos, and almost immediately it became one of the most feared asteroids ever discovered. For a brief period, it carried with it the possibility of colliding with Earth in the year 2029. The chance was not large, but it was real enough that scientists could not ignore it. Newspapers picked up the story, television segments followed, and for the first time in decades, the general public was faced with a serious, calculated risk of a cosmic disaster within their lifetimes. The first numbers suggested that Apophis had about a 1 in 37 chance of hitting Earth on April 13, 2029. Statistically, that was alarming, higher than almost any other near-Earth object ever tracked. If an asteroid about 370 meters across were to strike our planet, the damage would be catastrophic. It would not end life globally, but the impact would destroy entire regions, possibly cities, and trigger devastating effects far beyond the immediate site. Scientists rushed to refine their measurements, gathering every possible observation to reduce the uncertainty. Telescopes across the world were turned toward this one object, trying to determine whether humanity had less than 25 years before an unavoidable impact. The story of Apophis showed how fragile predictions can be when astronomers first spot a new asteroid. At the beginning, the orbit is not well known. A few dots of light on a few nights must be translated into a path through space, and even the smallest errors can lead to wide ranges of possible futures. With Apophis, those early measurements lined up with a dangerous path that intersected Earth's. The calculations were serious enough that scientists informed governments and space agencies immediately. For months, there was a race to refine the data, each new observation narrowing the asteroid's path. Slowly, the probability of impact dropped. By 2006, astronomers had gathered enough information to rule out a 2029 collision entirely. The asteroid would still come close, but it would miss. Even after the threat of a direct impact in 2029 was ruled out, there was still a small concern about what would happen during the flyby itself. Apophis would pass so close to Earth that our planet's gravity could shift its orbit. If that shift was just the right amount, it could send the asteroid on a return path that did intersect Earth in later decades. Scientists calculated a concept known as a keyhole, a tiny region of space Apophis could pass through in 2029 that would set it up for a collision in 2036. Once again, more observations were needed, and once again, the risks dropped lower and lower as the orbit became clear. Today, astronomers are confident that Apophis poses no danger for the foreseeable future. Even though the threat has been erased, Apophis remains one of the most dramatic asteroids humanity will ever witness. On April 13, 2029, it will pass just 31,000 kilometers above Earth's surface. That is closer than our geostationary satellites, the ones used for television and communications. For a body hundreds of meters wide to pass that close without hitting is extraordinary. People in parts of Europe, Africa, and Asia will be able to see it with the naked eye, moving across the sky like a fast-moving star. For planetary scientists, this will be a once-in-a-lifetime opportunity to study an asteroid up close without sending a spacecraft to it. Radar observations will map its shape in detail, and telescopes around the world will record every possible characteristic, from its spin to its surface features. The fear that Apophis inspired in 2004 also pushed planetary defense into the spotlight. Until then, the search for near-Earth objects was ongoing, but not widely discussed outside of science. Apophis showed that a newly discovered asteroid could raise alarm in an instant, and that more work was needed to track these cosmic neighbors. Governments and space agencies began to take the issue more seriously, funding better telescopes and international collaborations. The idea that Earth could be struck by a rock from space was no longer just a Hollywood storyline. It was a scientific reality that needed preparation. Apophis became the poster child for why humanity should pay attention. Every time a new asteroid is found, the cycle begins again. Initial worry, refined predictions, and usually relief. But the case of Apophis remains unique because of just how close the numbers seem to be. For a time, it felt like the universe had drawn a bullseye on Earth and set a date. When it was first discovered, there was no plan, no international agreement on how to respond. Should rockets be launched to deflect it? Should people be evacuated from likely impact zones? How much warning would be enough? These questions are still being debated today, and Apophis was one of the sparks that began those conversations. In 2004 and 2005, when the risk was still being studied, media outlets ran dramatic headlines about the asteroid that could end civilization. Later, when the risk was ruled out, Apophis became almost a celebrity in the world of astronomy. People began to look forward to the 2029 flyby, not with fear, but with excitement. Amateur astronomers marked their calendars and space agencies began to plan how best to observe the event. What started as a symbol of potential disaster transformed into a once-in-history opportunity to learn. When Apophis makes its pass in 2029, it will likely become one of the most watched objects in the sky. Telescopes on Earth will not be the only ones following it. There are already discussions about sending a spacecraft to rendezvous with it during its approach. The chance to study such a large asteroid up close, without the need for a distant journey, is simply too valuable to pass up. If that happens, humanity will not only witness Apophis's flyby from the ground, but also explore it in detail, turning what was once feared into one of the greatest scientific opportunities of the century. Methuselah, the star, seemingly older than the universe should allow. There is a star in the constellation Libra called HD 140283, but most people know it by a simpler name, Methuselah, after the biblical figure said to have lived longer than any other person. The reason for this name is not just its great age, but the fact that at one point, measurements suggested it might actually be older than the universe itself. That, of course, should not be possible. Nothing in the universe should predate the Big Bang, yet this star seemed to challenge that very idea. Methuselah is a faint star, visible with binoculars under good skies, about 190 light-years away. It is not large or especially bright, but what makes it special is its chemical makeup. Methuselah contains very few heavy elements, which is a sign that it was born early in the universe's history. Heavy elements like carbon, iron, and oxygen are built inside stars and spread through space when those stars die. The first generations of stars had almost none of these elements, and each new generation added a little more. Methuselah is poor in metals, as astronomers call them, which means it belongs to one of the oldest generations of stars. The problem came when scientists tried to determine just how old it really was. By using models of how stars evolve over time, astronomers calculated that Methuselah was around 14.5 billion years old. That posed a big issue, because the universe itself is estimated to be 13.8 billion years old. A star cannot exist before the cosmos that contains it, yet the numbers seem to suggest exactly that. At first, some wondered if this might mean the universe was older than we thought. The age of the universe is worked out from the CMB and from measurements of the expansion rate of galaxies. If those calculations were off, perhaps the cosmos was older, leaving room for Methuselah to fit within the timeline. But later studies of the background radiation with more precise instruments, like the Planck satellite, strongly confirmed the 13.8 billion year figure. The problem seemed to lie with the star's age, not the universe's. Determining the age of a star is not straightforward. Astronomers rely on several techniques. One is to study how bright and hot it is compared to models of stellar evolution. Another is to measure its distance and chemical makeup with great accuracy. Methuselah, being close to Earth, was a good target for such studies, but uncertainties remained. Even a small error in distance or brightness can shift the calculated age by billions of years. Later observations with the Hubble Space Telescope helped refine these measurements. Hubble was able to pin down Methuselah's distance more precisely, which allowed scientists to calculate its true brightness with better accuracy. When they recalculated its age, they found it was likely around 14 billion years, with a margin of error that could bring it down as low as 13.2 billion years. That would make it just younger than the universe, but still extremely old. The mystery was not fully solved, but the tension was eased. Methuselah was probably not older than the universe after all, though it had come close to the limit. What it shows us is how tricky it can be to measure stellar ages, and how even small uncertainties can lead to results that seem impossible. The case of Methuselah pushed astronomers to refine their techniques. Methuselah is moving rapidly across the sky compared to other stars nearby. This suggests it is part of the galactic halo, an ancient population of stars that orbit the Milky Way in long, stretched-out paths. These stars are some of the oldest in the galaxy, formed when the Milky Way itself was still coming together. Methuselah may have even been born outside the Milky Way, in a smaller galaxy that was later swallowed by ours. If true, it carries not just its own history, but the history of an entire lost system within it. Its low metallicity suggests it formed when there had been only 1 or 2 generations of stars before it. Those early stars must have lived fast and died young, spreading just enough material to seed Methuselah's birth. This makes it a kind of fossil from the dawn of time, a living remnant of a period we cannot otherwise see directly. By studying it, astronomers get a window into conditions that existed just a few 100 million years after the Big Bang. Even if its age now fits within the universe's timeline, Methuselah still stands near the very beginning of cosmic history. It is a survivor that has burned for nearly as long as time itself. When we look at it, we are looking at one of the first lights to shine after the darkness of the Big Bang. It is not hard to see why it captured so much attention. Gliese, 436b, the planet made of burning ice. Gliese 436b is a planet covered in water ice, yet hotter than a blazing furnace. How can ice exist in such heat without melting? The answer lies in conditions so extreme that they force matter into forms we never see on Earth. Located about 30 light-years away in the constellation Leo, Gliese 436b is what astronomers call a hot Neptune. It is similar in size to Neptune in our solar system, but its orbit is far tighter. The planet circles its red dwarf star in just 2.6 Earth days. That closeness means its surface temperature soars to around 400 degrees Celsius, hotter than an oven. By all common sense, water at such heat should not be solid, yet here it is not only solid but locked in place, forming something called hot ice or burning ice. The secret lies in pressure. On Earth, ice melts into water at high temperatures because the pressure is not enough to keep its structure together. But on Gliese 436b, gravity squeezes the planet with such immense force that water molecules behave differently. Instead of melting into a liquid or evaporating into gas, they are trapped in a solid lattice, even at scorching heat. The result is exotic ice that cannot exist under the mild conditions of Earth. Scientists call this state of matter ice-7, or superionic ice, depending on its properties. It is ice that burns. To stand there would be to see ice glowing with heat, an alien paradox. The outer layers of the world are thought to hold thick envelopes of hydrogen and helium, like Neptune. Beneath that is where the exotic ice forms, creating a deep ocean of frozen water trapped under pressure. Yet, unlike Earth's ice caps, this is not something you could touch or break apart. It is harder, denser, and stranger than any glacier on our planet. On Earth, methane clathrates, sometimes called burning ice, trap gas inside icy structures that can ignite when heated. On Gliese 436b, the concept is far more extreme. The ice itself exists in temperatures where ordinary fire could not survive. It is hot enough to vaporize metal, yet the pressure keeps it locked down. In a way, the planet is both burning and frozen, a contradiction made real by the crushing hand of gravity. Astronomers are fascinated by Gliese 436b not only because of its bizarre ice, but also because of what it reveals about planets in general. It shows that water, one of the most common molecules in the universe, can take forms far beyond what we see on Earth. Water may seem simple, solid, liquid, gas, but under the right conditions, it becomes something entirely different. If such states are common, then many exoplanets could have strange interiors filled with exotic ice, hidden beneath atmospheres of gas. These conditions might shape how planets form, how they evolve, and even whether they can host life in some hidden layer. Normally, planets so close to their stars become circular in their paths, because tidal forces smooth out irregularities over time. But Gliese 436b still has a slightly oval orbit. This suggests something is disturbing it, perhaps another unseen planet in the system. That extra push could be part of why the planet's interior is so stressed and unusual. The gravitational interactions may help keep its insides hot, maintaining the strange state of its ice. From Earth, astronomers cannot see Gliese 436b directly. Instead, they detect it through transits. By studying how the starlight changes, they can measure the planet's size, orbit, and even some details about its atmosphere. They know it has a puffy, extended atmosphere that seems to be leaking into space, stripped away by the star's heat. Yet deep inside, locked under incredible pressure, the burning ice remains. If you could somehow stand on a surface there, you would be surrounded by crushing gravity, immense heat, and skies filled with hydrogen gas. Beneath your feet, the ground would not be solid rock, but layers of exotic ice, glowing hot, yet unmelting. It would feel alien in every possible way. Life as we know it could never exist in conditions like Gliese 436b. But the fact that matter itself can behave so differently makes researchers wonder how many other surprises are waiting out there. Perhaps some exoplanets hold not just hot ice, but other states of matter we have not yet thought of. Dragonfly 44, a galaxy made almost entirely of dark matter. Most galaxies shine with billions of stars. Their gas clouds glow and their dust scatters starlight into faint spirals and streams. But some galaxies are almost invisible, not because they are small or far away, but because they are missing the very thing that makes galaxies bright: stars. Dragonfly 44 is one of these strange cases, a galaxy so dim that it was nearly overlooked. And yet, when astronomers studied it more closely, they realized that what it lacked in starlight, it more than made up for in something far more mysterious: dark matter. Dragonfly 44 was discovered in 2015 by a team of astronomers using the Dragonfly telephoto array, a set of telephoto lenses designed to spot faint objects in the sky. At first, it appeared to be just another small, fuzzy patch of light in the Comet cluster, a vast gathering of galaxies more than 300 million light-years away. But as the team studied its brightness and shape, they realized it wasn't just dim, it was unusually dim. For its size, it should have contained hundreds of times more stars than it did. The galaxy seemed to be a skeleton, a structure with the bulk of a large galaxy, but only a fraction of the visible matter. The real shock came when scientists measured how fast the stars within Dragonfly 44 were moving. The speed of those stars suggested that the galaxy had far more mass than its faint glow implied. In fact, the stars were orbiting so quickly that the galaxy should have torn itself apart if only normal matter were holding it together. The only explanation was that an enormous amount of invisible mass, dark matter, was providing the gravity needed to keep the galaxy intact. This finding was extraordinary. Dragonfly 44 appeared to have the same mass as the Milky Way, our home galaxy. But while the Milky Way contains hundreds of billions of stars, Dragonfly 44 has only a tiny fraction of that number. The rest of its mass, about 99.9%, must be dark matter. This makes it one of the most extreme examples of a dark matter-dominated galaxy ever found. To look at it through a telescope, it appears ghostly, a faint smudge compared to its brilliant neighbors. But behind that faintness hides an invisible weight far greater than its light suggests. Dark matter is thought to make up most of the universe's mass, yet it cannot be seen directly. Astronomers usually detect it by studying how galaxies rotate or how gravity bends light from distant objects. But finding an entire galaxy where dark matter so clearly outweighs normal matter provided a rare chance to study its role up close. It showed that dark matter is the backbone on which galaxies can form, even when stars are almost absent. Why does it have so few stars? If it has the same amount of dark matter as the Milky Way, then it had the same gravitational potential to gather gas and form stars in the early universe. But for some reason, it didn't. Perhaps its gas was stripped away by the Coma cluster's harsh environment before many stars could form. Or maybe a violent event like a burst of supernovae expelled much of the gas early on, leaving the dark matter halo intact, but the galaxy itself dim and starless. The exact cause remains uncertain, but the result is a galaxy that looks like a shadow of what it might have been. Another strange detail is the galaxy's globular clusters. Dragonfly 44 appears to have an unusually large number of these dense star clusters for its size. Globular clusters are often used to trace the mass of galaxies, since they orbit in the outer reaches where dark matter dominates. The abundance of these clusters in Dragonfly 44 helped confirm just how massive it must be, even though the galaxy itself shines so faintly. It is as though the galaxy invested most of its star-forming energy into making globular clusters rather than spreading stars across its disk. Dragonfly 44 belongs to a class of galaxies called ultra-diffuse galaxies. These are galaxies with the size of giants, but the brightness of dwarfs. They spread their small number of stars thinly across a wide area, making them faint and hard to detect. For decades, astronomers suspected such galaxies existed, but it wasn't until new instruments like the Dragonfly telephoto array came online that they were found in significant numbers. Dragonfly 44 quickly became the poster child of this group, a galaxy that looked like a wisp of smoke but carried the mass of a heavyweight. Some researchers have argued that the initial measurements of its mass might have been overestimated, suggesting Dragonfly 44 wasn't quite as extreme as first thought. Later studies refined the numbers, but even with adjustments, it remains clear that dark matter makes up the overwhelming bulk of its mass. Whether it is 99% dark matter or 90% doesn't change the fact that this galaxy is unlike almost anything else. Dark matter is often described as a hidden scaffolding of the universe, but it is rare to find an object that demonstrates this so vividly. Dragonfly 44 looks like a ghost in space, but its true weight is colossal, reminding us that what we see is only a fraction of what exists. Its nickname, sometimes called a ghost galaxy, captures its strange nature well. It is almost transparent, barely glowing, as though it were the outline of a galaxy rather than a full one. If the Milky Way is a blazing city in the night, Dragonfly 44 is a deserted town, with only a few lights left on, the empty streets held together by an invisible force. Looking at it is like peering into an alternate version of galactic evolution, one where light never took hold, but darkness still built the foundation. If galaxies like this exist in clusters like Coma, how many more are scattered across the universe? Could there be countless faint galaxies hidden in plain sight, too dim to detect but rich in dark matter? And if so, how do they fit into the story of cosmic structure? These ghostly systems may be telling us something fundamental about how galaxies form and fail, and how dark matter shapes the universe even when normal matter falters. ZTFJ 1901 plus 1458, the densest white dwarf ever found. When stars like our Sun come to the end of their lives, they do not explode in a brilliant supernova. Instead, they slowly shed their outer layers, leaving behind a small glowing core called a white dwarf. While not as dense as neutron stars, a white dwarf still packs more mass than the Sun into a sphere about the size of Earth. That means a teaspoon of white dwarf material would weigh tons on Earth. For decades, astronomers have studied these objects as the quiet embers of stars, stable and long-lived. But in 2021, astronomers discovered one that seemed to push the limits of what a white dwarf can be. It was given the name ZTF-J, 1901 plus 1458, and it stands out as the densest, smallest, and one of the most massive white dwarfs ever found. This white dwarf is located about 130 light-years away in the constellation Aquila. Most white dwarfs are about as wide as Earth, around 10,000 kilometers across. But this is less than half that, with a diameter of only about 4,300 kilometers, closer in size to our Moon. Despite its small size, it is almost as heavy as the Sun. Cramming so much matter into such a tiny sphere makes it one of the densest objects in the universe, just a step away from collapsing into a neutron star. The discovery of this peculiar star came from the Zwicky Transient Facility, or ZTF, a wide-field survey telescope in California designed to scan the night sky for changing or unusual objects. Astronomers noticed that ZTF-J 1901 plus 1458 was pulsing in brightness, flickering in a way that suggested it was spinning very fast. By analyzing the light, they realized it rotated once every 7 minutes, making it one of the fastest spinning white dwarfs ever observed. This rotation, combined with its extraordinary density, hinted at an unusual history. It likely wasn't just a normal white dwarf that formed after a single star's death. Instead, the evidence pointed to a cosmic collision. Astronomers think it was born when two smaller white dwarfs spiraled together and merged. In such a merger, the combined mass can sometimes be too much for a white dwarf to remain stable. If the mass exceeds about 1.4 times that of the Sun, the so-called Chandrasekhar limit, it usually triggers collapse into a neutron star or sets off a type of stellar explosion known as a type Ia supernova. But this white dwarf seems to sit right on the razor's edge. It weighs just under that critical threshold, massive enough to be unstable, yet not quite massive enough to collapse. Instead, it survived, leaving behind this shrunken, ultra-dense relic. This precarious balance is what makes it so fascinating. It reveals how thin the line can be between different stellar fates. Had its mass been only slightly greater, it would have collapsed into a neutron star, crushing its atoms into neutrons and becoming an object only about 20 kilometers wide. But it stopped just short of that transition. It is a cosmic tightrope walker, teetering between stability and collapse. Its extreme density suggests that the electrons inside are being pushed to their absolute limit, squeezed together until they are nearly indistinguishable. Any further compression and the forces that keep it from collapsing would give way. The idea that two white dwarfs can merge into a single object is important for another reason. Such mergers are believed to be one of the main sources of type Ia supernovae, which astronomers use as standard candles to measure the expansion of the universe. But ZTF-J 1901 plus 1458 shows that not all white dwarf mergers end in explosions. Sometimes they produce strange survivors instead. By studying this particular white dwarf, astronomers can refine their models of how stars live and die. Its rapid spin is another clue to its origin. When two white dwarfs spiral together, they speed up each other's rotation as they merge, much like skaters pulling their arms inward to spin faster. ZTF-J 1901 plus 1458 spins once every 420 seconds, an astonishing rate for an object with so much mass. This rotation not only keeps it stable, but may also generate powerful magnetic fields. Indeed, observations suggest that it has an unusually strong magnetic field, possibly 1 billion times stronger than Earth's. Such a field could have been amplified during the violent merger process, twisting and locking the star's interior into its current state. Many stars in the galaxy exist in binary pairs, and when both stars end as white dwarfs, their orbits can slowly decay as they radiate gravitational waves. Over billions of years, they can spiral inward and eventually merge. Depending on their combined mass, the outcome can range from stable white dwarfs to brilliant supernovae, or even neutron stars. Each possibility leaves a different imprint on the cosmos. White dwarfs cool over time as they radiate away their remaining heat, eventually fading into cold, dark remnants known as black dwarfs. But this star may not have such a quiet fate. Its density places it dangerously close to collapse. If it gains even a small amount of extra mass, perhaps by accreting material from space or colliding with another object, it could pass the Chandrasekhar limit and collapse into a neutron star. In that moment, its matter would be crushed into an object the size of a city, releasing enormous energy. It would be one of the rare cases of a white dwarf directly transforming into a neutron star without the spectacle of a supernova. In ordinary white dwarfs, the pressure that resists collapse comes from electrons packed so tightly that quantum mechanics prevents them from occupying the same space. This electron degeneracy pressure is what holds the star up against gravity. But in this star, the density is so extreme that the electrons are nearly being forced into the nuclei of atoms. This is the very edge of what white dwarfs can endure. Studying such an object offers a rare chance to test theories about matter under crushing conditions, far beyond anything we can reproduce on Earth. Its discovery was only possible because of modern sky surveys that scan vast areas of the heavens for unusual objects. Its detection shows that even in our galactic neighborhood relatively close to Earth, there are exotic remnants waiting to be found. As telescopes become more sensitive, more of these extreme white dwarfs may be uncovered. Some may sit just under the threshold of collapse, while others may be caught in the act of tipping over into neutron stars. In its tiny, super-dense body, ZTFJ 1901 plus 1458 holds the story of destruction, survival, and the narrow path between fate and transformation. Even after billions of years, the remains of stars still have new surprises to reveal. RxJ 1856, the featureless neutron star. The first thing to know about RxJ 1856 is that it sits in the constellation Corona Australis, about 400 light-years away from Earth. That makes it one of the nearest neutron stars we've ever found. Proximity is valuable because neutron stars are typically faint. Having a close example means we can study it in greater detail, pushing our instruments to their limits. When X-ray telescopes examined RxJ 1856, the readings showed a clean, featureless spectrum. Normally, astronomers expect to see absorption features caused by atoms on the surface or in the atmosphere of the star. Yet in this case, there were no fingerprints at all, almost as if the star had a perfectly smooth surface or an atmosphere that revealed nothing. At first, some researchers wondered if this might be a trick of measurement. Perhaps the instruments were missing fine details, or the models used to interpret the data were too simple. But repeated observations confirmed the strange result. Other neutron stars showed variety and complexity, but RxJ 1856 remained eerily plain. Its spectrum resembled that of a perfect black body, a theoretical object that emits radiation with absolute uniformity depending only on its temperature. Real stars usually deviate from that ideal. The smoothness of RxJ 1856 hinted that something unusual was happening at or near its surface. One idea is that RxJ 1856 could be coated in a thin atmosphere of hydrogen. Hydrogen is the simplest atom, and under the crushing gravity of a neutron star, it may strip away almost all spectral features, leaving behind something closer to a smooth black body curve. Another proposal is that perhaps RxJ 1856 doesn't have a normal surface at all. Instead, it might be what physicists call a quark star. In this scenario, the neutrons inside have broken down into their component quarks, creating a kind of exotic matter unlike anything we can reproduce on Earth. A star made entirely of this strange quark matter could emit light in a way that looks unusually featureless. If true, RxJ 1856 might be the first observed example of such an object. Of course, extraordinary claims require extraordinary evidence, and the quark star idea remains unproven. Yet RxJ 1856 has forced scientists to consider it more seriously than before. The smooth spectrum resists easy explanation. The debate is ongoing, and that is part of what makes RxJ 1856 so fascinating. It sits at the intersection of observation and theory, daring us to refine our models of matter under extreme conditions. The surface temperature measurements of RxJ 1856 suggest it glows at about 700,000 degrees Celsius, which is incredibly hot, though typical for a neutron star. But combined with its apparent radius, these values raise further puzzles. For a long time, estimates suggested the star might be too small to fit with standard neutron star models. If it truly were that compact, it could support the quark star hypothesis. Later, refinements in distance measurements adjusted the size upward, making it consistent with a more ordinary neutron star. Still, the possibility that it might harbor exotic matter lingers in the background, especially because the featureless spectrum is so unusual. Does its simplicity mean it is in a special stage of life, perhaps younger or older than typical neutron stars we observe? Or is it simply an outlier, shaped by unique conditions of its birth? Understanding this could shed light not just on RxJ 1856, but on the broader family of neutron stars, which includes pulsars, magnetars, and other extreme variations. Each of these classes tells us something about the limits of physics, from ultra-strong magnetic fields to rapid spin rates. RxJ 1856, by contrast, challenges us with its stark simplicity. The European Space Agency's X-ray observatory Athena, planned for the coming decades, could provide sharper spectra that might uncover subtle features we currently miss. Similarly, better measurements of the star's distance and size will refine our understanding of its structure. Until then, RxJ 1856 remains an enigmatic neighbor, close enough to study in depth, yet distant enough to keep its secrets intact. If RxJ 1856 truly hides exotic physics, it may be one of the few windows we have into states of matter beyond the reach of particle accelerators. That possibility alone ensures astronomers will keep returning to it, refining their instruments and sharpening their models. Whether it turns out to be a simple neutron star with a hydrogen veil or the first quark star ever discovered, its featureless face continues to stare back at us across 400 light-years, daring us to look deeper. Iapetus, the two-toned moon with a giant ridge, orbiting Saturn. Far beyond the bright rings, Iapetus is a world that refuses to be ordinary. At first glance, it might seem like just another frozen satellite, but a closer look shows features that no other moon shares. Its surface is painted in two extreme tones, one side gleaming like fresh snow, the other as dark as coal. And wrapped around its middle is an enormous ridge, a mountain belt that gives the moon a shape closer to a walnut than a sphere. These strange traits have puzzled scientists for decades, and they continue to spark new ideas about how such a bizarre body came to be. The brightness contrast of Iapetus is its most striking feature. One hemisphere reflects sunlight with dazzling intensity, while the other seems to swallow nearly all of it. Early astronomers noticed that the moon seemed to appear and disappear depending on its position in its orbit. When it faced Earth with its bright side, it was easy to see. When the dark side turned toward us, it nearly vanished. This suggested that the surface had two very different materials covering it. Later spacecraft images confirmed this. The bright terrain is coated in reflective ice, while the dark terrain is smeared with a material that looks almost tar-like. But where did this dark material come from? Some researchers believe it is dust swept up from another of Saturn's moons, perhaps the small and distant Phoebe. Others think it may be the result of radiation-driven chemistry, that changed the surface ice into darker compounds. Whatever the case, the contrast is dramatic, as though someone painted one half of the moon black and left the other half untouched. The darkening of one hemisphere may also explain why the boundary between the two sides is so sharp. Once a portion of the moon became slightly darker, it would absorb more sunlight, heat up faster, and cause nearby ice to sublimate away, leaving behind even darker residues. This created a feedback loop, making the dark side darker still, while the bright side stayed reflective. Over millions of years, this process carved the moon into its current two-toned form. The sharpness of the boundary is especially strange, running almost exactly along the moon's leading and trailing sides as it orbits Saturn. But the colors are not the only mystery. Perhaps even stranger is the giant equatorial ridge that runs around the moon's middle. This ridge is enormous, hundreds of kilometers long, towering up to 20 kilometers high, and stretching like a great seam across the world. No other moon in the solar system has anything quite like it. Seen from above, it makes Iapetus look like a walnut or a toy ball wrapped in a belt. The origin of this ridge is still debated. Some scientists think it could be the remains of a primordial ring system that collapsed onto the moon's equator billions of years ago. Others suggest it formed when the moon was still young and rotating rapidly, its surface bulging and freezing in place as it slowed down. Either way, it is a colossal structure that reshaped the landscape of the moon forever. For such a feature to exist, the moon's crust must have been able to support massive stresses without collapsing. That suggests that Iapetus cooled and hardened earlier than many other moons, preserving the ridge before it could relax or erode away. In some areas, the ridge appears weathered, with landslides cutting into its flanks. In others, it stands sharp and jagged, as if sculpted recently in geological terms. The sheer scale of the ridge makes it one of the most fascinating landmarks in the outer solar system. Beyond its surface mysteries, Iapetus also has a curious orbit. It travels much farther from Saturn than most of the giant planet's other large moons. Because of this distance, it moves slowly and takes more than 79 days to complete a single lap around its planet. Its rotation is locked, meaning the same face always points towards Saturn. Yet its tilted orbit and remote position suggest it may have had a different history from Saturn's other major moons. Some astronomers even wonder whether Iapetus might have formed farther away and migrated inward, or whether its strange features are tied to a unique set of conditions that no other moon experienced. The idea that Iapetus might have once hosted a ring is particularly intriguing. If early impacts around Saturn threw debris into orbit around the moon, gravity could have guided the fragments into a thin equatorial band. Over time, this band might have settled onto the surface, piling up to form the Great Ridge. If true, it would mean the ridge is a fossilized ring system, preserved in place rather than dispersed into space. When spacecraft such as Cassini flew past and sent back detailed images, many viewers were stunned by how alien it looked. Some even suggested that the ridge looked like a wall or an artificial structure. The unusual appearance of Iapetus makes it one of the more iconic and memorable moons in Saturn's vast family. Why do some moons develop such extreme features, while others remain smooth and uniform? What does the dark coating tell us about the flow of material through Saturn's system? And how could a ridge of such size have formed and endured for billions of years? Each answer helps build a larger picture of how the solar system evolved. By piecing together the story of one odd moon, we gain insight into the forces that shaped all worlds. TOI 1452b, the Ocean World Candidate. TOI 1452b is a planet slightly larger than Earth, falling into the category of a super-Earth. These are rocky planets bigger than our own, but smaller than the gas giants like Neptune. What makes TOI 1452b so interesting is not just its size, but its density. From the way it tugs on its star and the way it deems starlight during transits, astronomers can estimate both its mass and volume. those numbers suggested it isn't just a rocky planet like Earth, nor a gas-rich planet like Neptune. Instead, it seems to have a composition that points to a huge fraction of water. Some estimates suggest water could make up as much as 30% of its total mass. By comparison, water on Earth is less than 1% of our planet's mass. That means Thorne 1452b might not just have oceans, it might be an ocean world through and through. The thought of such a planet immediately raises images of endless seas stretching without land to break them. On Earth, oceans cover about 70% of the surface, yet continents and islands rise above the waves, creating a balance of land and water. On Thorne 1452b, the picture could be very different. It may have no continents at all, just a deep global ocean wrapping the planet in blue. The depth of that ocean could be hundreds of kilometers, far greater than Earth's deepest trenches. Beneath those waters, under immense pressure, strange forms of ice could exist, created by conditions unknown on our world. For scientists, Thorne 1452b is a prime candidate in the search for life beyond Earth. Water is considered the single most important ingredient for life as we know it. Every place on Earth where liquid water is found, life is present, from the deepest hydrothermal vents to the coldest Antarctic lakes. If Thorne 1452b truly is covered by a massive ocean, then it could offer an environment where life might emerge and thrive. Even if it looks very different from Earth, the chemistry of water could be a universal recipe. The planet orbits a red dwarf star, which means the habitable zone is much closer in. Thorne 1452b lies within this habitable zone. From its position, it receives just the right amount of energy for water to stay liquid, at least in theory. This is one of the reasons astronomers became so excited about it so quickly. There are challenges, however. Red dwarfs are known for their strong flares and bursts of radiation. A planet orbiting close to such a star might face powerful storms of energy that could strip away atmospheres or heat the surface in violent ways. Yet Thorne 1452b may have an advantage. If it truly has deep oceans and thick water layers, they could shield whatever lies beneath from radiation, offering stability where life could endure. The surface might be turbulent, but the depths could be calm and steady for billions of years. If Thorne 1452b is tidally locked, the global ocean could circulate heat between the two sides, creating complex currents and climates. On the day side, the ocean might shimmer under constant sunlight, while on the night side, frozen layers might spread across a dark surface. Somewhere in between, at the border between light and darkness, conditions might be most stable and potentially most friendly for life. For decades, astronomers wondered whether water-rich planets were common or rare. Discovering one so close, in astronomical terms, suggests they may not be rare at all. If Thorne 1452b exists, then surely there are countless others across the galaxy, each with vast oceans, each with the potential to host life. The thought of alien oceans is deeply stirring. On Earth, our oceans are teeming with life, much of it hidden far below the surface. Strange creatures thrive in complete darkness, feeding on chemicals from vents or drifting in the deep with bioluminescent glows. If Thorne 1452b has oceans even deeper than ours, what kinds of life might have evolved there? Perhaps simple microorganisms, invisible to the eye but vast in number. Or perhaps more complex beings, adapted to crushing pressures and eternal night. We cannot know yet, but the possibilities fuel the imagination. Hoag's object, a perfect ring galaxy. Hoag's object was discovered in 1950 by Arthur Hoag, an American astronomer. At first he thought he might be looking at a planetary nebula, or perhaps a strange quasar. But as more observations were made, the truth came out. It was a galaxy, but not one that fit neatly into any of the usual categories. Its central core of old yellowish stars was completely separate from a glowing blue ring made up of younger, hotter stars. Between them lay an eerie gap, almost empty, making the whole thing look like a cosmic donut. Spiral galaxies have arms that curve, sometimes symmetrically but never flawlessly. Ellipticals are smooth and rounded, but they don't have distinct rings. Ring galaxies do exist, but most are lopsided, distorted by violent collisions that push gas and stars outward. Hogue's object, however, looks as though it has been sculpted with care. Its ring is evenly spaced, its circle almost too neat, and its center clearly defined. It does not bear the scars of chaos that usually shape such systems. One of the leading ideas for how it formed is a galactic collision. In this scenario, a smaller galaxy might have passed directly through the center of a larger one. Such an event would send shockwaves rippling through the disk, pushing stars and gas outward to form a ring. Over time, new stars would light up along the edges, leaving the core intact and the ring glowing brightly. The problem is that most known ring galaxies formed this way look distorted or irregular, with off-center rings. Hogue's object, by contrast, is pristine. If it was shaped by a collision, it was an almost impossibly precise one. Another idea is that internal processes could have created the ring without the need for an intruder. Galaxies are not static. Their stars and gas can be shifted by instabilities in rotation. Some astronomers suggest that Hogue's object could be the result of an unusual gravitational resonance, where gas in the disk was drawn outward in a perfect circle, triggering star formation along the rim. This would make it a rare example of a galaxy forming a ring through internal dynamics, rather than through external violence. The yellowish light at the center suggests an older population of stars, similar to those found in elliptical galaxies. The bright blue of the ring shows the presence of hot, young stars, indicating recent star formation. This combination makes Hogue's object a kind of hybrid, an ancient galaxy at the center, surrounded by a youthful halo of fresh activity. It is as though two very different epochs of galactic life are frozen together in a single structure. When astronomers peer deeper into the background of the image, they find another surprise. Inside the gap between the core and the ring, far in the distance, lies another ring galaxy, visible through the empty space. This smaller, fainter object seems to mirror Hogue's object in miniature, a cosmic coincidence that only deepens the mystery. It gives the impression of looking into a hall of mirrors, where one perfect ring contains another. For scientists, Hogue's object is not just beautiful, but also useful. By analyzing its stars, gas, and motion, astronomers can test theories about how galaxies change shape over time. The sharp contrast between the old core and the young ring allows researchers to compare two different stages of stellar life in one place. It also raises questions about how stable such a structure can be. Will the ring remain intact for billions of years, or will it eventually collapse inward or disperse into space? Hogue's object is about 600 million light-years away in the constellation Serpens. That means we are seeing it not as it is today, but as it was when dinosaurs still walked the Earth. Across that gulf of time and space, its geometry has held firm, a glowing pattern untouched by the randomness of the cosmos. In a universe where chaos often rules, such precision feels almost miraculous. Looking at images of Hogue's object, one cannot help but feel a sense of calm order. The smooth ring, the glowing core, the black gap in between. It looks like a piece of cosmic art, hanging in the void. Whether it was born from collision, resonance, or some other unknown process, it remains one of the finest examples of symmetry in the universe. The Hercules Corona Borealis. Great Wall, the largest known structure in the universe. Stars already feel enormous compared to planets. Galaxies feel overwhelming compared to stars. And clusters of galaxies seem beyond comprehension. Yet even those scales, as vast as they appear, are small compared to the Hercules Corona Borealis Great Wall. This is not a wall in any familiar sense, but an immense cosmic structure, a gathering of galaxies bound together in a way that stretches across more than 10 billion light-years of space. It is, by current knowledge, the single largest known structure in the observable universe. Its existence raises questions that cut to the heart of cosmology, because according to our theories, something this large should not even be possible. The Hercules Corona Borealis Great Wall was first identified in 2013 through the study of gamma-ray bursts. When astronomers noticed a cluster of gamma-ray bursts in a particular region of the sky, the data suggested that an immense web of galaxies was present there, spanning a length on scales no one had expected. What was revealed was not just a single cluster, or even a supercluster, but something so vast that it broke the limits of what we thought gravitational structures could achieve. To understand why this is so shocking, it helps to think about the way the universe is supposed to be organized. On smaller scales, matter clumps together under gravity, forming stars, galaxies, and galaxy clusters. On larger scales, these clusters link into filaments, forming a web-like pattern, sometimes called the cosmic web. Between these filaments are enormous voids where matter is sparse. According to the cosmological principle, the idea that the universe is homogeneous and isotropic on the largest scales, structures larger than about 1.2 billion light-years should not exist. Beyond that size, the universe should look smooth, without massive clumps or walls. The Hercules Corona Borealis Great Wall is over 10 times larger than this limit. It doesn't just stretch past the boundaries of what we expected, it completely disregards them. Imagine trying to fit the Great Wall of China into the scale of human society, only to find out that someone has built a wall that circles the entire planet 10 times over. That is what astronomers faced when they measured the Hercules Corona Borealis Great Wall. If structures this large can exist, what else might be hiding beyond the edge of what we can currently observe? The Great Wall is located in the direction of the constellations Hercules and Corona Borealis, which is how it received its name. But its presence is not something we can see directly with the naked eye. To human vision, the region looks like any other patch of sky, dotted with distant stars. Only through deep surveys and the analysis of gamma-ray bursts do the outlines of the structure appear. Standard cosmology, built on the foundation of the Big Bang and the physics of dark matter and dark energy, predicts that matter should be evenly distributed on scales above 1 billion light-years. The fact that such a gigantic concentration of galaxies exists means that either the universe is more clumpy than we expected, or there are processes at work that we do not understand. Some astronomers have even wondered if the wall might be a statistical illusion, a coincidence in the distribution of gamma-ray bursts. But further analysis has strengthened the case that it is real, and its sheer scale continues to puzzle researchers. The Hercules Corona Borealis Great Wall appears to have formed relatively early in the history of the universe, meaning that galaxies were already gathering into massive structures when the cosmos was still young. How could gravity have had time to pull so many galaxies together into such a coherent shape? If gravity is the only explanation, then perhaps the initial conditions of the universe were not as smooth as we thought. Maybe the seeds of these massive walls were planted in the earliest moments after the Big Bang, imprinted into the fabric of space itself. Since dark matter makes up most of the mass in the universe, its invisible scaffolding determines how galaxies clump together. Perhaps the Hercules Corona Borealis Great Wall is a window into the hidden architecture of dark matter, revealing patterns that we cannot otherwise see. If so, studying this structure could give us new insights into one of the most elusive mysteries of modern physics. On Earth, we measure distance in kilometers or miles, and even our planet's circumference feels huge. In space, we use light years because ordinary numbers are too small to describe the distances involved. Yet, here we are faced with something that stretches 10 billion light-years across, a span that is itself comparable to the size of the observable universe. It is as though the cosmos itself is reminding us that our imagination, no matter how bold, will always fall short of its reality. The observable universe is limited by the speed of light and the age of the cosmos, meaning there is much we cannot see. If a structure this vast exists within our reach, who is to say what might lie outside it? Could there be even larger walls, filaments, or networks that dwarf everything we know? Perhaps the universe is not just vast, but layered with structures of scales we have yet to dream of. Each discovery of something larger pushes back the boundary of what we think is possible, reminding us that the cosmos does not conform to human expectations. And on that intriguing note, this journey comes to an end. What would you like for us to talk about next? Comment below, and if you enjoyed the video, consider leaving a like and subscribing to the channel. Thanks for watching.